Hello everyone and welcome to yet another recreational programming session with Mr. Zozin. And the topic of today's session is raycasting. Raycasting is a technique that allows you to create some sort of like a 3D perspective on a 2D map, and it was used in old games like Wolfenstein 3D. Right, so everybody knows about this game. It's an old famous game. Raycasting is what gives it this iconic look. So I never really implemented raycasting, right? But I kind of know roughly how it works. I know the main idea. And this is exactly what I want you to do on today's session. I want you to try to tackle this sort of technique and learn it essentially. So here I found a tutorial online. So I just googled up like raycasting and what kind of tutorials you can find online, and this was the first result in Google. And apparently it's a famous tutorial on raycasting. People told me it consists actually of 3 parts, right? So it goes quite into the detail of raycasting. I'm not going to be really strictly following it or reading into it too much. So I'm going to be just using the main ideas that I see on the pictures, right? So I think the pictures here are quite useful, right? So they actually explain you a lot. So I already tried to implement this topic online on Twitch, but I severely underestimated how complex that topic is and how much concentration it requires from me. So the entirety of the sessions were a mess, so I actually completely scrapped them and decided to start from scratch, but already offline, where there's nothing that distracts me, so I can fully focus on implementing raycasting. So how raycasting works? So essentially, you have a world that consists of a grid, right? So the world is the grid. And the size of the cell of the grid doesn't really matter that much. So, and because of that, it is easier to just pick the size of the cell equal to 1, because in that case, the cell sort of becomes like a normalized value from 0 to 1, which enables you to actually mapping that cell to whatever size you want, right? So it just like generally makes the math easier, right? So, and some of the cells here are marked as walls, as filled in, right? So let's actually mark this one as filled in and also mark this one as filled in. Maybe I should actually use something like this. Yeah, so let's just fill it in. I don't think I have a bucket. Maybe I do have a bucket, so maybe I can just use something like that. Right, so, but I mean, I already screwed it up. So yeah, we have a bunch of walls in here and stuff like that, doesn't really matter. And we also have a position of the player, and the player is not really snapped to the grid. The player can be like in between the cells and stuff like that. So let's actually place the player in here. And player is looking at a certain direction. And the player, sort of like the camera that is attached to the player's head, has a certain FOV, field of view. Right, so this is the field of view, and we also have a plane onto which we are projecting this scene, and this plane sort of represents this screen. So in essentially what we're doing, we are shooting the rays from the position of the player towards that sort of screen onto which we're going to be projecting things. Right, we're shooting the rays and we're trying to see what walls there intersect. So the walls usually have some sort of a color associated with them, right? So we see that this ray intersects with that specific cell with that specific color, right? And we basically take the column that is associated with this point on the screen, and we're just coloring that specific column on the screen with the color of that cell, right? So we're basically scanning vertically the entire screen. And that's how they used to do that. So because the scene is sort of like a very simple, you can just like, you know, scan with vertical lines and stuff like that. So it's pretty straightforward. So how do you shoot the ray? So you can do that with regular steps, but it's not particularly convenient because you can have some sort of like tunneling effects, like in this specific case. So what they suggest to do in here is to actually step with variable steps towards that snap to to the grid in here. As you can see, like each individual step, it just snaps to the grid. And that way we're being super precise and we never really overshoot or tunnel through the walls or anything like that. To be fair, I found this particular part of the entire technique the most difficult one, right? So because it has a lot of corner cases that you have to take into account. So, but I think off screen, I kind of figured out how to compress some of these corner cases. So I think it shouldn't be a problem on today's session. We'll see, we'll see. So I have a couple of ideas on how to manage the complexity of this entire thing. So, okay, we're going to be using JavaScript, right? So I haven't programmed in JavaScript for quite some time, so I decided to take this as an opportunity to sort of refresh that knowledge, right? So, and since I don't really like JavaScript as a dynamic language, I like to slap TypeScript on top of it, so we're going to be using TypeScript today. So let's go ahead and just initialize the project. So let me see. So this is array casting, right? And let's create HTML page as usual. So let me switch to an HTML mode. There we go. So we're gonna have a doc type HTML. So the first top tag we need to have HTML, and let's close it super quick. So the next tag we need is obviously head, right? So any HTML document consists of the head and of course the body. In the head, we're going to have the title. And the title is going to be equal to array casting in TypeScript. There we go. So within the body, we're going to have a canvas. We're going to be rendering everything on the canvas, at least for now. So once we implement the ray casting, we'll see maybe we can come up with something more interesting, right? So I don't know. So the idea of the canvas, let's actually say game, right? So it doesn't really matter. So we just need to have some sort of ID canvas. And let's also include the index JavaScript, right? So we're going to be compiling that index JavaScript from the index TypeScript. Okay, so we'll get this kind of thing. Let me do npm init, right? So let's initialize everything. So MIT, we're going to be using MIT license, and yes. Okay, so let me install TypeScript as a dev dependency. I think it's dev save, right? It's going to download the TypeScript and it's going to add it to the package.json, right, as a dependency. Is it dev dependency? I think it was. No, there were dev dependencies. Huh, that's bizarre. That's really weird. Is it save dev? Okay, so that's very. It's kind of funny how it didn't really complain when I did dev save, right? And it just did a completely different. That is absolutely bizarre. JavaScript. Anyway, so what we need to do in here, so let's actually call to the TypeScript compiler, right? So it's located in node modules.bin tsc, right? So the first thing we probably need to do, we need to initialize the config, right? So because it has a config of some sort where you can specify a lot of things. So we're going to keep it default, right? I don't really plan to modify anything. And let's actually enable the watch mode. But watch mode is only makes sense if we have something like index ts. So let's do console log and let's say hello world. There we go. So we have index.ts. If I start the watch mode, it's going to look into the current folder and it will find all of the TS files and convert them into the index.js, right? So this is the final thing. That we're also including into the index.html. So I'm not planning to actually start any server, right? So I'm going to just open index.html as it is. And let's actually take a look at the console, and there we go, here is hello world. Okay, so everything seems to be working, we have a working setup. On top of just watch mode in here, I think I also has some sort of like automatic LSP. I never really set it up intentionally, the only thing I did, I just installed a thing called Emacs Tidy, which is a TypeScript node for Emacs, but it comes with a pretty cool like LSP integration that just works out of the box. I never actually configured it or anything. Somehow it just figures out that you have a node modules in the current folder, and inside of these node modules you have .bin with a TypeScript compiler, and it just picks it up and just uses. So it's actually kind of amazing how it works. Anyways, so yeah, and it enables a lot of things. For example, jumping into the definitions of types and stuff like that, right? So I can do this kind of stuff. So maybe I should actually give the link to Emacs study in the description for anyone who's using Emacs. But it doesn't really give me like a direct link to GitHub. Maybe this is because it's DuckDuckGo. So it's a flight check lang. Yeah, so there's a tidy.el, but it's, I mean, there was a GitHub page somewhere. Why is that Emacs wiki? GitHub. Did they actually remove it? Am I using like a mode that doesn't exist anymore, or is this something wrong with Google? I don't really know. So let's actually go to Melpa and search in Melpa for this thing. It's so bizarre. Maybe I'm just using the extension that doesn't exist anymore and not supported. I could see myself doing that, and this entire thing is not like, okay, the entire infrastructure of Emacs is actually falling apart. Nothing works. Okay, so moving on. We don't really have that much time to wrestle with that. So anyway, so the first thing we need to do, we probably need to find the tag of the canvas. So let's actually wrap all of that into the lambda, right? So like so. So it always only runs, it only executes when everything is fully loaded. So and in here I'm gonna just do document get element by ID, right? And in here I'm gonna say find me the game. So I'm gonna just go ahead and print the game. There we go. So by default this entire thing actually returns HTML element, right? So but we will need to be able to do the following thing: get context, right? So and I can't do that because the HTML element doesn't have that methods. It's not the HTML element that has that, it's HTML canvas element, right? So we need to cast this entire thing to HTML canvas element. But here's this thing that kind of erases the information about the fact that this thing can be null, right? So I think it's more correct to actually cast it to something like this. So it's either HTML canvas element or null, right? So we're gonna do it like that. And so if I try to get the context, so I think I can even enable fly check mode. So yeah, it shows the errors and stuff like that. So yeah, game is possibly null. So we can just check if game is equal to null. Let's just throw an error, throw new error. We're gonna say no canvas with ID game is found. Maybe I'm gonna actually wrap it like that, and there we go. So, and in here we're gonna take the 2D context, right? So this is a 2D context. And it can also return null, as you can see. So we need to also check it. Equal to null, throw new error. 2D context is not supported for whatever reason. It's kind of weird. I think any browser these days will support this kind of context, but I mean, you never know. You never know. Anyways, so we've got the canvas and stuff like that. So some of the things I probably want to do, I probably want to set the resolution for the canvas. So as of right now, it just uses this default resolution which is 300 by 150, right? So let's set up something more like big. And I actually want to set up the square resolution. So because I want to play, I want to first start with this specific algorithm, because again, this algorithm is probably for me the most difficult part because it has a lot of different corner cases. So I really want to first nail that algorithm down, and as soon as we have it, we can continue with the rest of the Ray Caster, because I feel like the rest of the Ray Caster is pretty easy once you have this kind of thing. So it's sort of like the core, the essence of this algorithm, if you know what I mean. All right. So let's actually set the width and height. So I might as well actually set it to something like this. There we go. So let me see. So I'm going to refresh this entire thing. And what's the size? Okay, so the size seems to be appropriate, as you can see. The size seems to be appropriate. So we can't really see the canvas. So maybe it would make sense for me to, you know, color it with something. So we can do ctx fill rect, and we're gonna just say ctx canvas width, just fill the entirety of the canvas with a certain color, and we're gonna specify the color with fill style. So let's say it's gonna be something like 80 80 80. Let me refresh. Okay, so everything seems to be working. So let's actually align it, like center it horizontally and vertically. So let me go into the like index HTML, right? And let's maybe create the style tag, not really script tag, but style tag. So this is an ID, right? So that means we have to use hash in here. Okay, so if I remember correctly, so the easiest way for me would be to probably use position absolute, right? So we just have one single thing. It's just easier to do it like that, at least for me. So left is going to be 50% and top is going to be 50% as well. Okay, so we just centered the left top corner. Okay, that's fine. So, and I suppose now we can try to transform this entire thing and just translate -50 -50%. Is it going to work? Is it going to work? Yeah, it works. Okay, I still remember how to do that. That's cool. So now let's render a grid. Let's render a grid. So we need to decide the size of the grid. So let's actually say that grid rows is going to be 10. And let's also say that the amount of columns is also going to be the same. So it's going to be 10 by 10. Right. So now, after we render this entire thing, I'm going to iterate. So first I'm gonna probably render the vertical lines. So that means I'm gonna be iterating X, right? So I'm starting from 0 and I'm iterating grid columns, like so. So if I remember correctly, in the canvas, to draw the lines, you have to use this, like, you know, logo style graphics, right? So you have to do move to. First, you need to move your pen to a particular place. So let's actually move it to, in terms of X, it's going to be here. Right, but we also need to know the size of the cell. Right, so the size of the cell is 1, but when we are rendering it on the canvas, it has to have a certain size. So, and that size should be essentially, let me try to do that. So we're going to have cell width. It's the context canvas width divided by the green grid columns, and that's going to be the cell width. And we're also going to have something like cell height. Right, without these things we won't be able to properly render everything in here. So this is going to be the height and this is going to be the rows essentially. So this is going to be X multiplied by cell width, and since it's a vertical line, so it starts with 0 like this, right? And then we're moving the line, Emacs, why are you hanging? Okay, so line 2, essentially towards this. Yeah. So, but that's not enough. If you just do that, it's not going to show anything, so we can give it a try. But yeah, so we also need to specify the stroke style. So I think the stroke style should not be super bright. So let's make it a little bit like slightly brighter than the background. So let's say it's going to be something like maybe 30, 30, 30. Right. So you won't be able to see anything because you have to sort of like commit the stroke. Right. So once you do these actions, like as you do these actions, they just basically buffered, and to actually sort of like commit them, you need to do the actual stroke. I think this is how it works. And there you go. So we have a line on the left side, but we don't really have a line on the right side. So maybe we also need to say that X has to be equal. So we have a line here on the right side as well. So it's pretty cool. So we can repeat this entire thing for, you know, horizontal lines. So we're now iterating rows. And in here, I just move 2. So since it's a horizontal one, so it starts from 0, but it moves down, y multiplied by cell height. So we move 2, but then we line 2 context canvas width, and we just do this stroke like so. This one has to be white. Thank you so much, TypeScript compiler. And there we go. So we have a grid. So which is actually kind of cool. So now we need to specify like the position of the player, right? So I just basically want to define a point, and like which is going to be the position of the player, and display it on that specific grid. So to be fair, it would be nice to have some sort of a class vector2, similar to the one that I have in RayLib, right? So which consists of x and y. And also we probably should define a bunch of operations on this entire thing. Unfortunately, neither in JavaScript nor in TypeScript there's operator overloading, so we have to deal with methods, right? So which is a little bit easier than in pure C, but still not ideal. Honestly, for things like vectors and matrices in any language, there should be overloaded like plus, minus, multiplication operators and stuff like that. But anyway, so we're gonna have this component, so it's x and y. So this is x and y, and let's actually define constructor. Constructor x number, y number. So, and let's construct those things, right? So x and y, cool. So let's define a point, right? Let's define a point somewhere here. So this is going to be P1. We're going to have 2 points, right? So because 2 points will define the direction into which we are sending the ray, right? So because of that, we need 2 points in here. So the first point is going to be somewhere here. So the question is, in which coordinates do we want to have the point? I think we want to have it in world coordinates, right? So first of all, we have the world coordinates, or maybe it would be more correct to call them grid coordinates, right? So essentially, if you're standing inside of this cell, or maybe even in the center of the cell, the position of the player has to be 0.5, 0.5, right? So because the size of a single cell is 1. But we have another coordinate system, which is the screen coordinates. And as you can see, we're actually actively mapping the world coordinates, the grid coordinates, to the screen coordinates by multiplying by the cell width and the cell height and stuff like that. This is literally the reason why we're computing these kind of things. So, and if we're going to be keeping this kind of thing in the grid coordinates, if the position of the player, if the position of P1 is going to be in the grid coordinates, we also have to actively map it to the screen coordinates, right? So, and I could have some sort of a function that maybe just, you know, accepts, so map to screen, which accepts the context, the type of which is what. So it's a canvas rendering context to D. So I could probably do something like that in here, and also accept the point, and so say this function just returns a new point that is mapped within sort of this thing, and it also does the grid and stuff like that. It could work, but that means I'll have to constantly just call this function, and maybe that's fine, but I'm not particularly happy with all of that. So as far as I know, the canvas has ability to have transformations applied to it, if you know what I'm talking about. It has some sort of a transformations. And I always wonder, like, maybe I can use that. So let me see. So here's the context. I get the context within this thing. What kind of things do I have? All right. So, okay. So the canvas itself is just an interface, which is a composition of a lot of different things. So canvas compositing. So there's nothing interesting in here. Draw image. So maybe we need to have some sort of a transformations. Oh, okay. So the canvas transform. Okay, so here they are. You can rotate scale. Maybe this is what we want actually. Maybe what we need to scale. So essentially, if I just ignore this entire stuff, right? So if I don't do cell width and cell height, right, and I just like don't do any of these things, and I assume the grid coordinates. And because I assume the grid coordinates, the bottom one, right? So since it's an X, right, the bottom point in here has to be equal to grid rows, right? So that's the bottom one, right? If we're assuming that, and in here we just remove that, and this one gonna be grid columns, right? And we're also gonna remove that. So how is it gonna look like without? Yeah, okay. So it became super small. We can't even see what the fuck is going on in here, so it's insanely small. I suppose now what we have to do is to try to scale it a little bit, right? So if I just go ahead and do ctx scale twice, right? So if I scale it twice, okay, so it keeps increasing. But there's something kind of wrong with the size of the line. I wonder if you can do something with the size of the line in the context. That's a good question. So maybe something like line width. Okay, so there is a line width. So the cool thing is that like each field in here has a link to MSN or MDN. Yeah. So I confused MDN. Right. So, and it's a meter limit. This is not what I meant. God damn it. All right. So let me grab this thing. So this is a line width. Property of the Canvas2D API sets the thickness of the line. Okay, so this is probably what we need in here. Okay, so where is the scaling? CTX line width, and let's say this is going to be just like half of the line. So I just want to be able to see. Yeah, I think I see this specific. Yeah, this is good. I think this is good. So what if I put like 1 in here? Let's refresh. All right, that looks much better. So the question is, how much should I scale this entire stuff? So I feel like I should scale it by the size of the cell, right? So essentially, yeah, it's basically cell size, right? So I can do something like a grid. What is it called? So it has to be columns, and this thing has to be essentially grid rows. There we go. Is it going to work? Okay, it worked. So, and now I can just work with grid coordinates and don't really worry about this entire stuff. I wonder if I can just like make it, yeah, a little bit more thin. That's much better. Okay, I really like that. Okay. So, and now I want to draw a circle, right? So as far as I know, drawing a circle with the context is a huge pain in the ass. You have to like begin the path. I feel like you also have to begin the path like every time you even draw a line or something like that, but I don't remember if it's mandatory or not. Is it really mandatory? So let's actually take a look at the documentation. Yep. So let me see. So we can remove that, none of that is important. It starts new path by emptying the list of subpaths. Call the methods. Oh, okay, so essentially when you do move to line 2, it accumulates the actions. But if you want to kind of forget them, you want to do begin path. So it's not particularly necessary. I suppose it's cleaned up by things like stroke as well. At least I have a feeling that stroke also cleans up this buffer of actions. So maybe we don't even need to do begin path. Right, so method strokes are aligned to center in the world the stroke is drawn, which means the path intersection. They don't really, I didn't see them saying that they clean up the buffer of these actions. Typically you will want to call, okay, so this is where they're talking about it. Typically you want to call begin path for each new thing you want to stroke. If you don't, the previous subpath will remain part of the current path and get stroke every time you, oh! So I do need to do that. Okay, how this may be the desired effect. Yeah, okay. So I do need to do begin path every time I do one of these things. Okay, that's very interesting. So I suppose it was actually drawing the same thing over and over again, but because it's like the same thing, it's not really showing. So I wonder if it makes it more bright because of that. Doesn't really change anything. Anyway, so here we're studying the different path, and if I remember correctly, you just do arc. Alright, so and in arc, what do we have is basically the position of the center, right? So we can take P1, X, P2, Y, or P1, Y, Jesus Christ. So one of the things I like to do with Vector2 is just like introduce like a method array, which converts this entire thing into an array, like so. So then later I can actually just sort of like spread it. Not sure how more readable it becomes in here, but it just like allows me to do something like this. Yeah. So in terms of the radius, let's actually say that the radius is going to be maybe like 20% of the cell. So we have to specify two angles, so we're going to start from 0 to 2 pi, right? So the full circle, math pi. And whether it's a counterclockwise, it's actually an optional parameter, so let's remove that. So, and after that, we probably want to say fill. All right, so is it going to do anything? It's actually become darker, surprisingly. It's actually become darker. Interestingly, I probably need to specify the fill style. So let's specify the fill style, and let's use maybe purple color just to see what's good. Okay, so that seems to be nice. So purple is kind of dark. Let's use magenta. I think magenta is a little bit more bright. Yeah, there we go. So we have 0, 5, 0, 5, and yeah, that's the position of the player. That's pretty cool. Maybe I want to actually place the players somewhere in the center, like of the screen or whatnot. So it's going to be green columns, half of that, grid rows, half of that. So I want to do something like this, and it's placed in here. But maybe I just want to, I don't know, I can be creative in here. I can put 43 and just 33 in here, and it just can be somewhere here. It doesn't really matter. It doesn't really matter, I think. So anyways, that's pretty cool. That's pretty cool. That's pretty cool. So what I'm thinking, do I want to use vectors in here? Probably not, but it probably doesn't matter. One of the things I want to be able to do, I think I want to customize the second point, right? So if I'm going to be introducing the second point, like so, we can place it somewhere in a different place. Okay, let's actually factor this out into a separate function, because I don't want to be dealing with 3 lines every time. So let's say we're going to have a fill circle. We're going to accept the center of the circle, center vector 2. So this is a vector 2, so we're going to take the radius, which is a number. And we need anything else? We'll probably need the context. Yeah, sure. We'll probably need the context. What's the name of the context? It's a canvas rendering context. So this is another thing that we accept here as well. And as we're filling the circle, we are just doing that. Okay, so I can just do fill circle P1 02, and I think that's about it. So that's what I want to do. Fill circle. Oh yeah, provide the context. Thank you so much. So that enables me to just do something like this, right? So just a single function. Okay, so that's the second one. Cool. So I probably want to maybe do a similar thing for a line. I think it's gonna make it a little bit easier. So let's go ahead and do that. So it's gonna do function stroke line. So this is ctx. And we're going to accept 2 points in here, maybe P1 and P2. So P1 and P2. All right. So let's copy paste this entire thing. I have no idea what the fuck is going on outside, but whatever. So P1 array, we just spread this entire thing, and P2 array, and we also spread this entire thing. So, and I wonder how easy it is going to be to just use this entire stuff. So stroke line ctx, and now I need to convert all of these things into a vector. Will it be more readable? Maybe it will. Maybe it will. We'll see. So let's actually get rid of that. Is it working? Is it working? I think it in fact does. So stroke line ctx new vector 2. I'm gonna just grab this entire thing, place it in here, new vector, and then I'm gonna grab this entire thing and place it in here, and let's remove this entire stuff. Okay, so is it still working? Is it still twerking? It seems to be working, it seems to be twerking, so there's no errors or anything like that. This is pretty cool. Okay. So we can even maybe just use the stroke style of magenta, stroke style, and just like a stroke line from P1 to P2. So now we have a line between them. That's pretty poggers. So we never really specified the width, the thickness of the line. Maybe this is something that we should do. I mean, it's specified through the line width of the like above, so I think it's fine. Okay, so we have 2 points, right? So we have 2 points, and one of the functions that I want to do that will allow me to sort of like a step with the ray is the function that accepts both of the points. So let's call it something like ray step. So it accepts p1 vector, p2 vector, and I think it should return you the third line, which is right. So if this is the first point, p1, and this is the second point, the third point should be an intersection with this side of the cell, right? So it finds the first intersection and gives you the third line. So then you can now use the next pair of points to find another one that intersects in here, and so on and so forth. So this is the kind of function that I think I need to implement something like this. Right, so this is basically what we need. So right now I don't know how to implement that, so I'm gonna actually just return p2. So interestingly, for the sake of like debugging and simplicity, it would be kind of cool if I could customize p2. So maybe what I want to actually bind p2 to a mouse, right? So let me see, can I just take the context and add event, it doesn't have event listeners, so I think it's this thing that has event listeners. All right, so what kind of events listeners do we have in here? Event HTML event map. All right, so we have element event map, full screen change, this is not what we want, global event handler. Okay, so here they are. So mouse move. This is probably the one that we need in here. Okay, so mouse move. And in here we're gonna have an event. Right, so, and this entire thing, event, what does it have? So position, it's kind of hard to tell like what is this thing. So does it have anything? Okay, so there's a client X, so it's a mouse event, all right. So what kind of things do we need in here? Offset X and offset Y. So I think that's the things that we probably want in here. So I might as well just take a look at them. Console log event offset X, event offset Y. Let's take a look at them. So you probably want to open the DevTools so we can see Scheiße. Okay, so that's pretty cool. So this is 800, 800, and this one, the upper one has to be 0, 0, if I understand correctly. So I can't really seem to get what I need. Okay, so this is very close to 0, 0, but it doesn't show me. Oof. I guess it's fine. Right, so but that means we'll have to map this entire thing to the world coordinates ourselves. Right, so we have to map it to ourselves. We can probably maybe take the following thing. So I can construct a new vector2 out of this entire thing, and I wanna divide it by the size of the canvas. So we probably need a divide operation in here. So let's actually quickly introduce that. So it's gonna take the second point, so let's call it that, and it's going to return this. So let's implement. So it's going to be vector2, this x divided by that x, this y divided by that y. So that's what we need in here. So this is the position of the mouse. We divide it by excuse me, new vector, which is the size of the whole canvas, right? So we have to do ctx canvas width, ctx canvas height. So this is a little bit too much. Honestly, I would like to maybe factor it out to a function that just allows me to do canvas size, right, and it just returns the vector2, and it just accepts something like this, right? So it accepts the canvas, and it gives you the size of the canvas as the vector, right? So we have to actually return this entire thing in here. right, as the vector, so you can then reuse it, because I feel like we're going to be using this a lot. Right, so this is going to be canvas size, ctx, and there we go. So that thing is normalized actually from 0 to 1. It is normalized from 0 to 1. We have to remap it to the grid coordinates. To remap it to the grid coordinates, we have to actually multiply it by something like grid calls and grid rows. Yeah. So let's implement multiplication. So this is another thing that we'll probably need in here. So this is multiplication. So this is that. And this is that. Okay, so we take the offset of the mouth, we divide it by the canvas size, and we multiply it by this entire thing. Maybe it would be better to actually define something like grid size, which is, yeah, something like this. But that means we have to actually define it after in here, right? So because vector 2 is not defined yet. So let's log this entire thing. So I'm gonna actually assign it to maybe p, and let's see if it corresponds to what we need. So this is 0, this becomes 1 1, kind of, but it's not fully where I need it. That's so bizarre. Is it really, so is it really the offset I need? Because it's kind of, yeah, it's missing 1 in here. Why is it missing 1? I have no idea, but this one is 10 10, so it's missing. Maybe that row is not really visible there or something. Don't really know what the fuck is going on, but it seems to be that offset is fine. Maybe because it's, oh no, I thought maybe it's because of the zoom of some sort. Anyways, whatever. So let's try to do the following thing. That's really bizarre, actually. It kind of bothers me, because this has to be, can I maybe zoom out like really a lot so I can see what the fuck is going on in here? So is that 0 0? Okay, so it is 0 0. So that means we just didn't see one row in here. Okay, so so I want this thing to be like undefined by default, so maybe I can put this thing somewhere here. Right, so initially it is undefined, and then later we just assign it to p2 like so. Okay, so let me see. Cannot read properties array full circle. Okay, so I see what is going on. So I think we have some, yeah. So this thing is equal to undefined. Yeah, the type of this entire thing is undefined, and it will be only defined when you move for the first time. Okay, so that makes sense. So I feel like we have to say that the type of p2 is vector2 or undefined, and initially it's going to be undefined until you move a little bit, and it will be assigned to something new. And while it is undefined, right? So if p2, let's say, is not undefined, only then we're going to try to render it. Right, only then we're going to try to render it. So if it's undefined, we're never going to even try to render it. So that makes sense, I think. Okay, so that doesn't work for some reason. Why doesn't it work? Because we need to... Oh, Jesus Christ. We have to re-render the whole thing. We have to re-render the whole thing every time the mouse moves. All right. So that means I need to factor out the whole thing here into some sort of separate function that does the rendering and shit. All right, so function grid or something, might as well just, you know, grab the whole thing in here and just like copy paste it somewhere there. So where's the function grid? Let's put it in here. What is it complaining about? Is it complaining about ctx? So let's pass the ctx in here, sure. What is it complaining about now? P2. So we can also pass the P2 as well. Okay, so that actually makes a lot of sense to pass P2 in here and also say that it could be vector or undefined. So it's either vector or undefined. So here, what we're going to be doing, we're going to be doing grid ctx p2, right, and every time we move this entire thing, we re-render ourselves again. Okay, so that's basically what we want. Okay, so that actually looks kind of nice. Okay. Oh, okay, so damn. It's probably because we're doing some transformations and like, yeah, so Canvas is extremely stateful. It's almost like OpenGL, right? So we're messing with the state. So maybe we should save the state or restore it and then restore it. Or maybe you can just do something like, do you have, okay, so there's a reset. Okay, canvas state. This is a canvas state. So can you just, what does reset mean? What does reset mean? Method of Canvas Studio resets the rendering context to its default state, allowing it to be reused for drawing. Okay, so this is precisely what we want. Okay, that's cool. So I suppose first thing we can do before rendering this entire stuff, we reset the state of the canvas and then we render the whole thing. Okay, so this works. I'm really happy. Okay, so yeah, so we have the position of the player and we have the custom thing. And what I want to do, honestly, in here, if we have P2, of course, I want to just do array step P1, P2. Does this thing, okay, so this is the only thing that accepts, and I want to have P3. So, and in that specific case, we can even connect P2 to P3. So this is a stroke, but we might as well also render P3, like so. So we compute the third one, and I want to just keep rendering it as sort of like a way to, you know, to debug this entire stuff. We can even try to do something. So essentially I can always do P2, subtract P1. Do I have a subtract? I don't even have subtract. Okay, so let's implement this operation. Let's implement this operation. Sub is going to be minus, is going to be minus. Cool. So where is the ray step? So I'm subtracting it. Maybe I want to normalize it. Do you even have a normalize? Okay, so I don't have a normalize. Norm. So going to take this thing. So to normalize this entire thing, we just need to take the length of the vector, right? So this is going to be this length, which doesn't exist, right? So we have to implement this entire thing. So it's going to be a number. It's a number. So what's going to be the length? Well, I mean, you just take this x multiplied by itself, or you just want a square, then you take the square of y, and you just do sqrt. There we go. So just return this entire thing. So this is the length. And essentially what you want to do, you want to just take each individual component and just divide it by length. All right, so this is going to be something like that. So new vector2, and you just return the whole thing. Okay, that's cool. But then you can have a situation when L is equal to 0, right? So you don't want to have a division by 0, so maybe you want to actually explicitly check if this thing is equal to 0. What do? I guess you just return like a 0 vector, if that makes any sense, right? So, because I mean, it's a 0 vector, there's nothing much you can do in here, right? Anyway, so raise step, so you normalize this entire thing. We can now scale this entire thing maybe by half. Right, and we could just return that, so that way you have sort of the next step. Yeah, we don't have scale. So let's do scale. So we have a value, which is a number, and you return a vector2, so you just do new vector2, this x multiplied by value, this y multiplied by value. There we go. Is that a Gucci? Is that a Tamaguchi? I think so. Right, so that is absolutely freaking bizarre, my friend. Why is it so fucking bad? Why is it so fucking bad? So yeah, this is because I actually wanted to add P2, right? So because we just have the difference in here, right? So then we normalize the difference, so it's just the direction. Then I like elongate the direction to half of a cell, right? Or I elongate it to half of a cell. To be fair, originally it's more like 1, so maybe I don't even have to elongate it, right? So let's not elongate it. So we also need to have an addition. All right, so I'm going to put it in here. So this one is going to be add, and let's replace minus with plus. Ah, you didn't replace shit, bruv. bruv. Okay, so what else do we have in here? Does it work? Does it work? It does in fact work. It does in fact work. So as you can see, so it renders this third sort of cell. All right, so that's pretty cool. So we have a setup for testing in chat. I would like to make a small break and refill my cup of tea. Right, and after the break, I'm going to try to implement Ray step. So probably the most difficult function in here, right? So the one that basically steps this way, right? It finds the nearby sort of border or boundary and just snaps to that. So it's kind of like not really obvious how to exactly do that, but I have a couple of ideas that may help us. All right, so let's make some break and all right, I'm back. We need a linear equation. So what is a linear equation? It's an equation that has the following form. Y is equal k multiplied by x plus c. So essentially, if you know these two parameters, k and c, of a particular line, you can take any x on the plane and you can instantly find y that basically gives you a point on that specific line, right? So essentially it's like a black box, right? So you plug x into it and you instantly get a y associated with the line. So if you have 2 points, right, P1, which is basically x1, y1, and P2, which is x2, y2, you basically end up with a system of 2 equations where y1 is equal k, x1 plus c, and the same thing for the second point in here. So and essentially, by solving this equation for k and c, you can find those parameters. You can actually find them. What we can do here, we can actually take the first equation, right? So and we can figure out c from that equation. We can just like move this thing on the left side, and that's about it. So we basically got c. So this is our c. So now we can take that c and actually plug it into the second equation, right? Like so. So this is what we have in here. And you may notice a very interesting thing, right? So we can take k and move it outside of the parentheses. And now we can move y1 here, like so. So this is going to be negative. And now we can just divide this difference of y's by the difference of x's, like so. And this is how we find k. So k is usually called slope, and sometimes I see on the internet, specifically in Wikipedia, it's called m, but I kind of got used to calling it k, so it doesn't really matter. So this is how you find these parameters for if you have these 2 points. And we do in fact have these 2 points, so that means we can actually easily find any other points on that specific line. Right. So, and this is precisely what we want to do in here, right? But we don't really want to find like arbitrary points in here. We want to actually move along the line in the direction of that line, in the direction of the ray. We know the direction of the ray because of the order of P1, P2, right? So essentially we know that the ray moves from P1 to P2. So we know precisely the direction of the ray. So, and we want to actually snap to the closest boundary of the grid. So and the question is, how can we even figure out the closest boundary of the grid? This is actually a very interesting question. So essentially, if you know the direction of the ray, right, so you can basically find the boundary horizontally, the horizontal boundary, right? So towards that direction, and sort of like a vertical boundary, right? So essentially, if I have an x and y, I can relatively easily find, so where is the next x towards that direction and where is the next y towards that direction. But that kind of gives me 2 points in here. So if I just snap to here, okay, so here's the first point, and I can snap to here, which is the second point. Which one should I pick? I should probably pick the one that is closest, right? So essentially what we have to do is so take the closest x boundary and y boundary and pick the one that is just closest to the current point. So that's probably what we have to do. So but the question is like, how do you even find the closest boundary if you know the point and you know the direction? That's a very interesting question. So let me grab my paint and let's take a look at some sort of a grid. Do I think what did I do? I can't draw in here for whatever reason, even though this layer, okay, so this layer kind of weird. So it's a group layer, I cannot draw here. Anyway, whatever. So I have a cell within which I have a point, right? I have the current point. So, and I also have a certain direction. So if the direction of X is positive, so what's interesting is that we can know the direction of the ray by looking at the deltas of Y and X. In fact, quite often these two differences are denoted as delta Y and delta X, right? So we can do something like this. So this is delta Y and this is delta X, like so. So it's a delta Y and delta X. In fact, I can already compute them. So I can maybe create something like D, P2 subtract P1, and there we go, I've got the deltas. So now, if dx, right, if dx is positive, right, so if the dx is positive, that means that the whole thing moves to the right, and in terms of X, the closest boundary is the right one. Which means that to snap for this thing to that boundary, we just have to take the seal of X. Right, we have to take the seal of X. So what's interesting is that if the direction of the whole thing was something like this, dx would be actually negative. Right, because in terms of X, we're moving to the left, so dx is negative. So in that case, we have to pick this boundary. So that means we have to actually do the floor of X. So depending on the sign of dx, we have to do either seal of dx or the floor of dx. So, and this creates like a lot of combinatorial complexity, right? So you need to consider cases when dx is negative and dx is positive and so on and so forth. So what's interesting is that as soon as we know dx and dy, right? So d contains both dx and dy, we probably want to actually compute the slope, right? So, and the slope is just y divided by dx, but it only makes sense if dx is not equal to 0. So if dx is equal to 0, you have a division by 0, so you can't use this formula. But if you have dx equal to 0, that means you have a vertical line, right? And following a vertical line is actually pretty trivial. You don't even need the equation of the line, right? So you have to consider whether if dx is negative, if it's positive, or if it's equal to 0. So you can also consider different situations when for example, dy is 0. It's a separate kind of situations. If dy is 0, k becomes 0, which doesn't create any problems unless you want to kind of invert the linear equation, right? So where's the linear equation? So I already removed it. Linear equation allows you, given x, find y, right? But who said that you can't kind of invert it? So essentially move c to here, right, and then maybe divide by k. So, and that gives you the formula that given y gives you x. But look, that doesn't allow you to find x if k is equal to 0. So that means you have to consider separate situations for when x is equal to 0, if it's less than 0, if it's bigger than 0, and also if when y is equal to 0, because if y equal to 0, k is equal to 0, so this formula stops working. So you also need to consider a situation when y is negative or positive because of the symmetrical situation with snapping floors and seals and stuff like that. It's a freaking mess. Whew. It's a freaking mess. So I'm pretty sure the tutorial actually suggests something smart, but the problem with this tutorial is that it has a lot of text. I can't bring myself to read that. Yeah, so they're doing some sort of like step -1 + 1, and it's just like, I don't want to read all of that. I honestly don't want to read all of that, so yeah. But I came up with an interesting idea. So what if we just abstract away the, decision whether to use floor or seal depending on the direction of the dx. Right, so we can actually quite easily abstract that away. So let's create some sort of a function. So something like, let's call it snap. Right, and so it's gonna work with either x or y. It doesn't really care, right? It just works with one of the components of the vectors. What it accepts x, right? So that specific x that you want to snap towards, towards left or right or up or down, it doesn't matter. And it also accepts the difference, right? So because that delta denotes the direction, right? That delta denotes the direction. So, and this entire thing obviously is going to return a number, right? So, and essentially what we have to take a look at, we have to take a look at the sign of the whole thing. So if dx is positive, so that means we move in a positive direction. So we move right to the right here if we're looking at the x. So that means what I have to do is return floor x. That's what I have to do. Okay, cool. If dx is less than 0, so that means if it's positive, I think I have to do seal. Yeah. So if it's positive, I have to do seal. Right, because I'm gonna be, so I'm moving to the right, so it's increasing. So to snap to this thing, I have to do seal. Yeah, that makes sense. Almost made a focky in oopsie doopsie. Right, so in case if it's negative, we move in the other direction. We snap it to the left. If it's equal to 0, exactly, we just return x. There is nowhere we can snap things to. So, and that kind of simplifies these two things, because now, right, so let's see. Let's actually get rid of the k. Right, let's remove all of that stuff. And if dx not equal to 0, right? If dx is not equal to 0, we can easily compute k. So we can just easily compute k, and k is dy divided by dx. Very, very cool. And as soon as we can compute k, we can also compute c. So both of these things are immensely helpful in here. So this is P1. So I can actually do something like this and then something like this. So we have now both C and K. So, and now what I have to do, I have to take the second point, the point of P2, right? I need to take its X, and now I can just snap its X to the correct boundary based on the DX. And that gives me sort of like an x3. So it gives me the x of the next the next point of P3. And once I know x3, I can also compute y3, right? Because I know the linear formula. So I can just plug x3 multiplied by k plus c, and there we go. I've got the third point. I actually got the third point. Might as well just return it, right? So let's go ahead and just do x3 and y3 just to see what's going on in here. So in case of dx equal to 0, I suppose we can just return p2 as a sort of like a stopgap. Right, okay, let's take a look at the application. All right, look at that. It is actually snapping, but only horizontally, right? So it snaps only to this thing, right? It kind of works. We have this situation when dx is actually, yeah, so when dx is equal to 0, there's nothing much you can do, right? So there's nothing much you can do in here, but that's kind of funny. Yeah, that's pretty cool. So, but we also need to snap to y, right? We also need to snap to y because we just need to pick the closest point, right? So how can we, I kind of want to visualize both of the points, the x snapping and the y snapping, but I only return one points. How can I return 2 so I can visualize both of them? You know what I'm thinking? Maybe I should allow array step to visualize the points itself, right, for debug purposes. Let's actually allow it to visualize the points itself, right? So this is, I'm gonna just return nothing in here, and I'm gonna do ctx, maybe even fill circle ctx new vector2 x3 y3, and I don't remember what was the radius. Okay, radius was this, and we also probably need to do fill. So fill style, let's say that the fill style is going to be red. So we're just like doing this thing, and let me see if it's working. If it's twerking, it is not working, it is not twerking. That is bizarre because I actually called this function incorrectly, right? So yeah, that makes sense. So I have to do ctx in here. Alrighty, okay, so it actually renders 2 points. Why the fuck does it render? I think I know why, because it modifies the strokes, fill style in here, fill style. Yeah, that's what's going on in here. Yeah, okay, that's cool. So this is the first point, this is the X point, so to speak. I don't really like that it's kind of big. I would like it to be like half of this size. Did you not? The fuck, bruv? So why is it so? Is that because we never actually use the radius in here? Look at that. Maybe I should go through all of the errors. So flight check next. Okay, so there's no errors anymore. Cool. Okay, so that's a little bit smaller. So yeah, let's visualize the second point here as well. So the second point is y. So what we have to do, we have to take p y, and we need to snap it according to its direction, according to its current direction, and this is going to be effectively y3. So let's actually scope this entire thing a little bit, like so, right? So they do not interfere. So once we have y3, we can try to find x3 by using the inverted formula. Right, where's the inverted formula? Here is the inverted formula, like so. So let's say it's x3, y3, but you have to be careful in here, again, because k can be equal to 0. It's equal to 0 when dx is equal to 0. So one of the things we can do here is maybe if x is not equal to 0, right, if it's not equal to 0, and by the way, I should probably use the double equals here as well. We just do that. And we can now draw the second point in here too, but let's actually draw it with a different color so we can distinguish them. There we go. So look at that. We're moving in that direction. So towards that direction, we're snapping to one side, to the vertical line, and we snap into the horizontal one. So, and we end up with 2 points. So what we have to do now, we have to pick the one that is closest. So that's what we have to do. I think in here, it's relatively easy to do if we just maintain something like P3, and we say that initially P3 is equal to P2. But then, as we snap X, we can say, okay, P3 now, temporarily, is this. It is this now. Then, once we figured out that k is not equal to 0, we have another candidate for P3. So it's actually called P3T or something, right? So, and this is going to be something like this. And we have to just pick the one that is closer to P2. Right, so we should be able to do something like P2 distance to P3 T should be less than this distance to P3. And if it is, the new P3 is equal to P3T. So, and we just return P3, something like this. But we need to implement distance too. For the vector 2, of course. So here we're going to accept the second vector. So the thing we're going to do, we're going to just do that sub this, and we just take the length. So that's the distance, and we have to return that, and it's going to be a number. There we go. So does that work? Does that work? That seems to be working. So interestingly, maybe we wanna disable the debugging of these things, right? So, and in a place where we do ray step, okay, so we're already rendering this entire thing. Okay, so as you can see, it is picking always the closest one, except when dx is equal to 0, because we never really handled that situation, right? We never really handled that situation. Yes. Okay. So let's quickly handle that situation, I suppose, when dx is equal to 0. So it should be relatively straightforward, I think. Right, so when dx is equal to 0, we just need to basically snap only y, I think. We need to snap only y. And since we are moving vertically, right, either down or up, the x is going to be basically equal to, yeah, the x is going to stay the same, right? So basically x3 is p2x. So that's it. That's what it is. So, and since this entire thing was never executed, the new p3 is going to be literally that, I think. I think that's how it's going to work. So x3, y3. So that's basically the case in here. And yeah, so if it's, did it work? Yeah, I think it worked. So when dx is equal to 0, that works, and that always picks this kind of situation, right? So this thing actually reduces like a lot of combinatorial explosion in here, actually. Just moving this out into a separate function, right? Depending on the dx, whether it's negative or positive, just do either ceil or floor. It helps tremendously, actually. It helps tremendously. So we don't really need these debug things anymore. Let's remove them. So, but we want to actually continuously step, right? We want to continuously step until we encounter a wall or something. So where is the example? I don't really know where it is. So maybe it's somewhere up there. Yeah, there we go. So as you can see, we want to continuously step and snap towards the boundaries like so. So that means ray step has to be called in a loop, right? So how can we approach that? So let's literally put it into the loop. So maybe I'm gonna even say that this is gonna be a let, so it's gonna be modifiable, right? Because as soon as we can compute the third point, I want the second point to become the first one and the third one to become the second one. If that makes any sense. I'm not sure if it does. But anyway, so let's say that we're gonna do one single iteration in here, just one single iteration, like so. And we just rendered everything like that. So let's not render this. So afterwards, I'm going to say P1 becomes P2 and P2 becomes P3. Right, so we compute the next one and yeah, everything seems to be fine. So this is a single iteration we're doing. This is a single iteration and doesn't do shit, honestly. That's bizarre, my friend. What the fuck is going on? Raise step because P2... the fuck? So what if I do 2 steps? Maybe that's what's going on? Yeah, apparently I need to do 2 steps. That's really weird. Oh yeah, I understand why. Because the first step just renders this point and a connection between P1 and P2. Okay, that explains it. So that means you need to do 2 iterations in here. All right, so that's fine. So the most interesting thing is that what's going to happen if you want to do the third iteration? It doesn't really go any further. Because this entire idea with snapping only works if for unsnapped points, right? So as you can see, after the first iteration, this thing is already snapped. You're trying to snap it again in that direction, but it's already snapped. There is nowhere to go. Like it's already snapped, so it's gonna stay the same. So it works only for the first step where this thing is unsnapped, but then it cannot go any further. It just can't go any further. Sad. Truly freaking sad. So one way we can do that, before snapping it towards certain boundary, we can actually just try to push that value towards a direction a little bit. right? So if it's already snapped, we want to just push it over the edge. So essentially, like we have this thing in here, we're trying to snap it towards the direction, it's already snapped, there's nothing we can do. We can just add like a tiny little bit of an epsilon in here so it goes over this edge, and that will actually force it to snap to the next one. So that's one of the things we can do in here. We can even maybe pass that epsilon, I don't know, we can maybe bake that epsilon in here. So let's actually say, we don't really need this like a super high precision or anything, so 1/1000th of 1. 1/1000th is 1/1000th of 1. I don't know what I'm talking about. How can we step in that specific direction? So we kind of need to normalize dx. But what we can do, so in JavaScript there is a math sign. It just gives you the sign of the thing, and it's going to give you either -1 or 1 or 0 depending on the value of dx. So, and we can just multiply it by the epsilon, right? So that automatically kind of steps towards the direction with a little bit of the step in here, with a little bit of the step. So yeah, maybe I'm gonna still accept the epsilon. I'm not really sure how exactly I want to approach that. So the next error, so we don't really use this shit anymore, so let's remove that. Next error, okay, snap. So let's maybe bake epsilon in here. So this is going to be epsilon 1/1000th. So this is the epsilon that we're passing. This is another epsilon that we're passing. The next error, we don't pass ctx anymore. Next error, no errors. Okay, cool. Does that solve the, it does. It does actually solve the problem. Right, so as you can see now, it can actually step precisely as in here. Right, so that's how we can even do all that. So that's pretty cool. So we actually do a limited amount of steps, array step. So where do we do array step? So we can like increase the amount of steps just to debug things, right? So now we do 5 steps. Right, as you can see, sometimes it goes really far. Oh, no, I mean, yeah, that makes sense actually. So that allows us to kind of jump really, really fucking far. But I mean, yeah, that is kind of cool, isn't it? That is kind of cool. So maybe the next thing we want to do, we want to try to allow to go until it goes completely outside of the thing. That would be an interesting question, but how can we even do that? So essentially, how can we know what cell the current array points to, if you know what I'm talking about, like what cell it currently points to? So essentially, we have this array. So this is P2, right? So this is P2. P1 is somewhere here probably. So this is P1. So it means the direction is in here. Like, how can we know that we're inside of this cell? So given this point, we need to somehow find this point. Right. So we can floor both x and y of this value, which will make P2 snap to this point. But then in terms of y, it's already snapped, so it will never snap to here. So we can do a similar trick we did in here, right? So basically push it towards a direction with a little bit of an epsilon and then snap both x and y to here. So that way, if you're colliding with a certain sort of thing, you know the cell you're currently hitting at. So yeah, that's pretty cool. And it probably will work even if you're inside, right? So if you're inside, you're still pushing towards direction, you're still gonna, okay, so that I think that seems to be the case. How are we gonna be doing all of that? So essentially, maybe I want to have it as a separate function. So we have a snap function cell hitting cell, right? And so in the place where we're going to be using all that, we don't really have a dx. All right, so we don't really have a dx. So I think we're going to accept both p1 and p2. Right, so it's going to be both p1 and p2. So the thing we can do in here, we can compute d, so which is p2 sub p1. Right, we kind of need to do that. Right, and then we can essentially push p2 towards a certain direction. So we do p2 x plus math sine dx. So we need to have an epsilon somewhere here. So this is the epsilon. So we multiply by this epsilon. So we're just moving this kind of stuff towards that. And then we want to floor the whole thing in here. And that gives us like the, you know, the x of this cell. So, and if we repeat that for y, we can just straight up return a vector 2 out of this entire thing, like so. So that's pretty poggers, I think. That's pretty poggers. So we hit in the cell and we need to post an epsilon. Honestly, let's actually make the epsilon like a global constant of some sort. I think, yeah, I think that's a good idea. So APS, we just don't do that. Right, so the next point, we don't have to pass that. Next error, we don't have to pass that. Right, and we don't have to pass that, and that's it. So the thing I want to do in here is basically, let's just go indefinitely, right? So we're going indefinitely, and then for the second point, what we're going to be doing, so hitting cell P1, P2, right? So, and we basically have this kind of thing. So hitting the cell, so yeah, we don't have to accept the epsilon, so we made it a global value. So, okay, so we have C. And essentially, I want to break when C is out of bounds, essentially, right? So if C is less than 0 or C is greater or equal to grid size X, or C, it actually has to be X, right? It has to be X. So the same thing has to be repeated for Y. Y is less than 0 or CY is greater or equal grid size Y. And so here we can just break out of this entire thing. So I just want to stop at that specific thing. We can also now introduce some sort of a map which denotes whether something is a wall or not a wall, and also stop at walls. Right, but let's actually first check the boundaries. I hope it's not going to go into the infinite loop or anything. Okay, so that is a little bit bizarre. I don't really know why it doesn't... Yeah, why does it stop? So I would expect it to at least maybe allow to go there. So if P2 is already looking, if it's already looking at something, okay, maybe it should not be P2, right? Maybe it should not be P2. Maybe it has to be more like P1, but I'm not 100% sure. Yeah, because it doesn't make any sense, honestly. So we're pointing at the X equal to 0. Okay. So, but that should create the next thing. I think I know what is going on. I think we have to do this check after we rendered something. Yeah, okay, that explains. Okay, so it was a rendering bug, actually. It was a completely rendering bug. Cool. So now we're tracing all of that shit up until the out of bounds stuff. That is super cool, believe it or not. That is insanely cool. All right, so let me maybe introduce the scene, so to speak. So we have a grid, rows and columns. So we have grid, rows and columns. So we probably need to do this weird node stuff, right? So I can always create like a 10 elements in here, like 10 elements. And I can't even fill the, well, I can fill this kind of stuff maybe with zeros. But interestingly enough, right, so I can't fill this entire stuff with another array of tens. Tens which are filled with zeros. I can't really easily do that because if I modify this thing, so if I just assign this thing to 1 and take a look at that, right, as you can see, rows, they share the same thing, which is not particularly great, I think. I don't think it is particularly great. So what we have to do, we have to actually map each individual element to this entire thing, but we actually have to fill this entire thing with something first, right? Only then it is going to work like that, right? Because arrays have like empty elements or something like that. I don't really know how JavaScript works and I don't really care. So we kind of want something like this in here, right? So this is what we kind of want. And so here we create this amount of rows and this amount of columns, right? So this is what we have, and this is basically a scene. Right, so this is basically a scene, but maybe this scene has to be initialized somehow, somewhere. I don't really know where, but we should probably try to initialize it. So for instance, I maybe want to set the scene 1 scene 1 to 1, right? So, but we won't be able to even see anything in here because we don't visualize these cells like at all. So visualize the grid, right? So we visualize the grid, but nothing much. So I think what we have to do in here, we have to, before we render the grid at all, we have to iterate all of the rows, right? So we're iterating grid rows, like so, and then iterate the columns and Emacs. So this is the columns, this is X, right, and if scene Y X is equal to 1, or maybe let's say not equal to 0, right, so not equal to 0, we have to draw the rectangle of some sort, right, so ctx fill rect, and let me think what we want to do in here. So maybe I'm going to actually put this as a fill style. So this is our fill style, and we're filling in fact X and Y with the size 1, 1, right? So because everything is normalized right now. So yeah, there we go. So as you can see, we have a wall. We have a single wall. One of the things we can do now, one of the conditions to stop the ray tracing, ray casting rather, is not only when we out of bounds, but also when we hit one of the walls, right? So after checking all of the bounds in here, right, so in here we are 100% sure that Cx and Cy is within the bounds, so which enables us to do something like scene Cy Cx equal to 1, right? If it is equal to 1, we're just breaking out of this entire loop, like so. Look at that. So this is basically the exit condition. This is basically the exit condition. So let me see. It doesn't fucking work. So I wonder why. Because I forgot to save this entire shit. Okay. It works. So yeah. We have a working ray casting algorithm. So we can cast arrays and they stop at walls and shit. They stop at walls and shit. So it would be kind of cool to actually have arbitrary scenes in here, right? So as you can see, scenes right now, they have to be specifically square, which is a little bit annoying, honestly. Which is a little bit annoying. So if I make it like non-square, right, so 10 by 20, so it becomes something like this. But this is entirely like a rendering bug, so it's kind of understandable. So what I'm thinking is maybe what we have to do, we have to turn this entire thing into a minimap, right? So because we're just like rendering the internal representation of the scene and stuff like that, but this is not like a real ray casting, right? So we haven't got into like actually getting something like this on the screen like whatsoever. We're just like figuring out the math. And as you can see, math is actually kind of finicky, right? So it's pretty nasty, honestly. So there's a lot of corner cases and stuff like that, and it's just like, kind of meh. So we need to have both of the views, and we need to have this sort of view and the view of the actual rendering. So what I'm thinking is that I want to turn this entire stuff into sort of like a mini-map. I wonder, yeah, this one is rather weird. Yeah, I mean, if it tunnels through, there's nothing much you can do anyway. Right, so I want to turn this into a mini-map. So let's call this a mini-map. So a mini-map. Let's go to the compilation errors. Okay, so this is just a mini-map. On top of this being a mini-map, I think we have to specify a rectangle on the screen into which we have to fit the entirety of this thing. Right. So let me see. So I think it's gonna be I don't know how to call that. Maybe it's gonna be a boundary, right? And it's going to be basically an array of two vectors, right? So it's going to be vector 2 and vector 2. So it's going to represent the position of the left top corner, and then the size of the boundary. It's basically a rectangle. So that's what I want in here. And on top of that, I think I also need to accept the scene, right? So I don't want this scene to be like hard-coded like this. I want the scene to be passable to the thing that renders the minimap. So let me quickly see what I can do in here. So this is the scene. And how do I do that? Is that, do I have arrays in TypeScript? Yeah, I do have arrays. So I can say it's an array of numbers, right? So I can maybe even factor out that into a type, but I don't really want to do that. As of right now, at least. So what I want to do, I want to get rid of all of this stuff. Right, so because for the longest time we had these grids like sort of hard-coded. I want to unhard-code all of that stuff. All right, so let's go to the compilation errors. So we have a boundary which is unused. That's fine. Okay, so here's the scale. Okay, so we can. So we take in the entirety of the thing. But to be fair, I think what we have to do is we have to take the boundary size. So let's say that we're going to have it as a position and size. And this is the boundary. So we're going to destructurize it. Which kind of hints that maybe we should just pass this as a position and size. I don't really know why I grouped all of that like this. That's kind of weird. Yeah, and this is the size, so which is a vector 2. All right, so this is position and size. So the way we need to scale all of that stuff, we just need to take the size, I suppose, and divide it by grid columns and grid rows, which is basically the dimensions of the scene. So we need some sort of a function, I don't know how to call that, which accepts the scene, which is this. You know what? Let's factor this type out. So we're gonna say that type scene is that. So this is the scene, this is the scene. And it just returns you a vector which is the size of the scene. Okay, size of the scene. Size, scene size. There we go, I figured that out. So, and it returns you some sort of a vector. Can I just assert something? I don't know, so it's console assert. Console, hola. So does it even work? So conditions. Is there something like to do? I wonder. Transform two documents, so it's not really to do. I was thinking it's just like I want to crash. I think I can do something like throw new error, like to do scene size. I don't want to implement it right now, so I just want to kind of postpone the implementation for a little bit later. So here we have a size, the size of the whole boundary, and I want to actually divide this entire thing by the scene size. And we provide the scene, so it computes the size. And that's how I want to scale this entire thing. I can actually do something cool, I think. I can take an array, right, and I can literally spread this thing in here. Yeah, boy. So we're scaling it like that. So now this one is actually getting interesting. So what I'm thinking is I want to have something like grid size. So it's a scene size. So this is a scene size. Scene, I said. So I can reuse this thing in here. So this is a grid size. So that means now I can do grid size Y. And this is grid size X. Alright, so what's the next error? Go to the next error. Alright, so columns is X, so this is a grid size X, and this is grid size Y. Alright, so what do we have in here? Okay, so this one is pretty straightforward, I think, because I can just do grid size. I can just do grid size multiplied by this vector, essentially without the grid rows or any of this bullshit. My friend. Okay, so that's pretty cool. That's pretty cool. By the way, on top of scaling this entire thing, so since the minimap has a position so it can be placed anywhere on the screen, I think on top of scaling this entire thing, we also need to do translation. Does it do translation? So you can translate. Okay. So let's give it a try. But I'm not actually sure. Right. So we first probably want to translate the whole thing. So we take the position and array and translate it and then scale it. Not 100% sure, or maybe first scale it and translate it. So, like we should expect that there will be some sort of bugs when we first try this kind of thing, right? So because I'm not sure in which order we have to do. I feel like I first use scale and then translate. I think, right? Because, yeah, I think it makes sense. Whatever, we'll see. So the next error that we have in here. So this is a grid rows, which is grid size Y. And this one is a grid size X, What's cool about the statically typed compiled language, right, is that like I can just follow the compilation errors and automatically refactor everything. Compiler assisted refactoring. So yeah, that's pretty cool. It would be kind of nice if I could just like quickly check that something is within a certain boundary. I wonder if I can have something like I don't know. So let's not do that. So yeah, I think it would be easier to just keep it like that. Yeah, I think I'm already overcomplicating. Yeah, so it's I didn't even have to modify this thing too much. I don't know. Keep overthinking as usual. So here's the thing. Now I should be freaking able to do this kind of stuff where I can just have this thing and have a bunch of these things in here, right, with arbitrary shapes and stuff. And I can just like place arbitrary walls in here. Just to test how this whole thing works. Yeah, so let's go to the next error. So grid columns. Ooh. Okay, so this one is rather interesting. So because we're specifically like mapping. Yeah, so now, yeah, this one is interesting. So we have, I think this thing has to be square. So it's a 4x4. And in here we have to have a grid size or maybe scene size. So, and this is the scene, and that should give us the thing. So, okay. So in terms of position, this has to be 0. Maybe let me create a second constructor, something like static 0. Which is going to return vector 2, and that is going to be new vector 2 0 0, right? So I want to be able to do this kind of thing. Vector 2 0. Okay. So, and in terms of the size, I think, do you have a canvas size? Yeah, I do have a canvas size, perfectly. Canvas, canvas size, let's just do CTX. Right, so that's the position I have in here, so, and then I also specify the scene. Yep, that's it, so I can repeat this thing here. Okay, so I refactored it a little bit, so now scene is kind of replaceable, but it has to be specifically square, otherwise it's going to be distorted when displayed in here. So let me see, and it doesn't fucking work, I wonder why. So does it say any errors? Okay, so, sure. Scene size, okay, so let's go ahead and implement that. So the Y is pretty straightforward, it's just a scene length, that's the Y. We can put it like this even. So X is a little bit more interesting, I think, because it's basically the maximum row within the scene, I think. I think that's how we should consider the maximum row within the scene. So we have to maybe take the minimum value, so number min value. So let's iterate through each individual row in here. Let row of scene, right, and basically we can do math max x row length. Length I set. So now we should be able to just return the vector 2, x and y. So that's the size of the scene. Right. Refresh that, and that seems to be working. That seems to be working. Look at that. So we have this thing, and this seems to be working. Yeah, but it's too small, honestly. It's too small. But it's customizable now. It's immensely customizable, so I can just do something like this. Right, so this is basically plus 3, 1, 2, 3. So we have 7 columns and 7 rows. Okay, so that allows us to do something like this. But the initial position of the player, is kind of sus, if you ask me. So, and for some reason it's also defined in here. I have no idea why it is defined in here. Maybe you should actually define it in here. So, and minimap should accept the P1 as well. Alright, so let's go to the next error. This thing is never used. Grid size. We actually compute grid size if you think about it. Grid size. So we can do const grid size, like so. So P1, canvas. Is it really grid? It has to be canvas size. I don't know why I decided to do it like that. It's a canvas size. All right, are you happy? Oh. So what was doing? So why did I replace this thing with grid size? I don't fucking know. Let me see. Yeah. Something is terribly wrong. One more time, but with a passion. So grid, we're gonna say scene size scene. Alright, that should be basically enough. P1, yeah, so it's not available. P1 vector, minimap, P1. Alright, so are you happy now, my friend? Okay, so that's cool. So the reason why I was doing that is because now I can customize quite easily where we're gonna move all of these things. So maybe I'm gonna say 6, 4. There we go, so that makes more sense, I think. Might as well actually move this entire thing closer to the borders and stuff. That, yeah, so, and in terms of here, so maybe 93, yeah. So that looks much better, I think. Yes, look at that, that's pretty cool. So we already can scan the whole thing in here. That is fucking epic, mate. That is fucking epic. So again, we can't really, you know, have rectangular maps because they're gonna look like scheiße. Look at that, they look like scheiße, but I mean, it's just like a display bug. It's kind of a display bug. What's funny is we can actually display these things smaller, right? So let me try the following thing. I'm gonna have a minimap position, right? So minimap position is just a vector 0, and minimap size. So the minimap size is just a canvas size. CTX. Emacs should back up Emacs. Emacs should fork mate minimap size. This one is minimap position. So minmap. Okay. So what if I scale this by half? Became smaller. So what's funny is that the mouse is not properly mapped and shit. The mouse is not mapped and shit. So we have to map it differently. So we used to divide it by the canvas size. Now we have to divide it by minimap size. That's right. So yeah, that works and shit. So that works. But now, what if I want to offset the position? So essentially, I can maybe add. So we have a canvas size, CTX, and maybe scale it by 10%. Right. So I want to just. Jesus, bro. Okay, so that was a mistake. I didn't think that was a good idea. So let's try to slowly offset this entire thing. So what if I just offset this entire thing by 1 pixel? All right, that didn't change that much. So what if I offset it by 10 pixels? It goes forward too fucking much. And I wonder if this is because of how I do the translation and scaling. What if I do them in a different order? That makes more sense. So, as already said, right, I expected this to have some bugs because I can never remember like whether you translate first or scale first or something like that. I can never freaking remember, mate. I can never freaking remember. So what about 100? Okay, so that's cool. But now the mouse is offset. The mouse is offset. So one of the things we probably have to do, we have to maybe subtract. So we have to do the same thing in here, like scaling and translation and stuff, right? So, and I wonder if I have to subtract it or maybe add. We'll figure it out. Yeah, I just had it to add, subtract it. Okay, that's perfect. So that means now I can place this minimap like anywhere, and then in the background have an actual rendering. So I kind of have separate rendering of the scene and the minimap of the scene. So this is actually super convenient, I think. This is actually super convenient. So let me take the canvas size. So this is going to be canvas size, CTX, and I want to scale it maybe by like maybe what should I call it, like 10%. So that's going to be, yeah, the offset. But also I'm not kind of sure. So what if it's that? Yeah, this is not good. Yeah, so that's the size of the minimap. And the padding has to be, yeah, that's good. I think that's good. That's a good one. So that's a good minimap. One of the things we can do now, I think, we can try to add a support for rectangular things. Right, so I'm not sure if how visible it is. Is it really visible? I think it's not particularly visible. So let me try to maybe increase the line width twice. Yeah, I think it becomes better. So maybe even 6. Yeah, boy. So I think it's more visible. Let me see in OBS. Yeah, I think in OBS it's actually visible. So maybe even 10. Oh yeah, look at that, bruv. Okay, so how are we gonna approach this entire stuff? So instead of like computing minimap size in terms of canvas size, let's compute it in terms of the cell size. Let's introduce the cell size. And the cell size, let's say that is going to be ctx canvas width, maybe like you know, 10% of the shit. And what we're going to be doing is actually we're going to take the scene size, right? So this is a scene size of the scene, and we are multiplying it, actually scaling it by the cell size, and that's basically the size of the minimap. Right, so, and it retains its shape. It retains its shape. Yeah, so that's actually perfect. That's actually perfect. That's all of the math works out, surprisingly. All of the math works out. So yeah, now I can actually have arbitrary shapes instead of maybe I'm going to do it like 4, and it's a proper minimap of sorts. So maybe I can reduce the padding in here. So yeah, I can control all that. So, and now in the background I can have something else. And to be fair, like I don't really need to keep the game square, right? So I can just use 800 by 600 and it's still going to work fine, I think. I think it is still going to work fine. Maybe we can even use like a 16 by 9, you know, ratio in here with a certain factor. Factor multiplied by factor. It doesn't have to be super big, I think. So it could be something like 50 maybe. Maybe even closer to 80. Yeah, that's much better. And I want to reduce the cell size in here, maybe 2. That's too much actually. What about 3? It scales way too quickly. Yeah, it scales way too quickly. Okay. That is a pretty poggers. That is pretty poggers. So I'm already streaming for 2 hours. I think the time has come for another break. So yeah, as you can see, this particular thing is actually very fucking complicated. And this is what I was talking about at the beginning of the session, right? So I just, like, I really underestimated how many small little things there is in raycasting. So you can explain the idea of raycasting on a piece of paper, on a napkin, right? So, but then if you like sit down to implement it, there's a lot of different things, and you need to have like special things to debug all of that stuff, right? And for the longest time, you won't be able to even see anything on the screen, right? So you're just messing with the geometric stuff. It's really freaking surprising. Like, I really underestimated this problem. So anyway, I want to make a small break. I want to refill my cup of tea, and after that, we're gonna try to finally render something on the screen. Like, god damn. So anyway, let's make some break. All right, I'm back with my tea. So let's continue. What do we need to do? I think the time has come to finally introduce the notion of the player. I think it's kind of crucial to have a player in here. So let's create a class, right? So player, and what player is going to have? It is going to have a position where the player is located currently, and I suppose also a direction where the player is currently looking. So let's put it like this. We probably need to create constructor for this entire thing. So position, we're going to specify the position, the direction, which is just a number, and then this position, this, and then we're gonna do direction. Position, direction. So now I suppose this is what we need to have instead of P1 and P2, honestly. Right, so let's actually create the player, and this is gonna be a new player. The position, let's say, is going to be this. So this is the position. Direction, let's put it as 0. So, and that kind of means that I have to get rid of this entire stuff, right? So, and I suppose minimap now should accept only the player. Alright, so this is what we're going to have in here, but the definition of the player is down below. So, but I mean, maybe it's like just hoisted automatically. I don't have to worry about this kind of stuff. Yeah, probably don't have to. So, what do we have in here? So here is the player. And what I'm passing in here is just the player. All right, so that makes sense, hopefully. Now, so grid. Yeah, actually resetting the whole state of the context just on a minimap is kind of bad, I think. So what would be better, in my opinion, is saving the state and then restoring the state. I feel like Canvas has this kind of stuff. Yeah. So you can save it and then you can restore it. I suppose it works like a stack of some sort. Let me actually see. So save a method saves the entire canvas by pushing the current. Okay, so okay, that's pretty straightforward. All right. So we can just do something like save, and then at the end of doing all of this stuff, we just do ctx restore. Cool. So it just cleans up everything after itself. So that means we can have separate function that renders the scene, like just does ray casting, and it has its own state and stuff like that. And minimap is not gonna ruin that state. So we have a bunch of errors, which is fine. So let's actually go through them. So this is the next error, the next one. So we fill the circle. So we probably need to just fill the position of the player, right? So, and we don't have a P2, so that's about it. Next error, so we ran out of errors. Very cool. Right, so here's the position of the player. It doesn't really have a direction or anything like that, but maybe we should render that direction, right? So it would be kind of nice to maybe have something like a vector2 from angle, where I could just do player direction. So, and then, yeah, just render that as a second point. So maybe even take a player position, add the whole thing, and then from angle, maybe scale that. We can scale it by what? We can scale it by the nearing clipping plane. So essentially, just a second. Here is the position of the player. Might as well want to take something like this. So this is the position of the player. The player has a certain direction it's looking at. So, and when we're doing ray casting, we also have a certain, like a plane onto which we are projecting everything. So when we are rendering the direction the player looking at, we might as well actually take the length as the distance between the player and that clipping plane, that projection plane. So we probably want to define it somewhere. So we have this epsilon. Let's introduce near clipping plane, which is going to be maybe half of a cell, because why not? So this is what we're going to have in here. So minimap, where is the player position, blah, blah, blah. So we scale it by near clipping plane, and we still don't have a from angle. So let's introduce that. So we're going to have a static from angle. We accept the angle, which is a number. We return vector2, and we just return new vector, which is basically cosine of an angle and sine of an angle. There we go. So that's pretty cool. So that gives us the point towards which we want to stroke a line, I think. So we stroke line from player position to this specific point that we constructed in here. So we also have to pass the ctx, of course. Okay, so we can see some shit, but it's not really colored properly. So we have to do stroke style like so. Yeah, so that looks fine, I guess. That looks fine for now. We can increase the minimap for now so we can see some stuff. Just make it bigger. That's too big. A little bit smaller so it fits into the screen. Right, so and we can experiment and stuff like that. So let's maybe move the player in some different place. What about 63 by 63? Just I want to move it closer to here. Okay, so let's rotate it and make it look at these obstacles, right? So if I rotate it 90 degrees, so this is just the position, and here we're gonna have math. Pi is basically half of a circle, right? So I need to take half of a pi. So that rotates it like, yeah, because the coordinate system, that's understandable. So what about 1? Okay, and we can maybe multiply it by 125, like a little bit more. So now it is looking towards that. So maybe near clipping plane. What about 75? So I want it to be a little bit bigger. So yeah, it is now a little bit bigger. So that's pretty cool, you know. But we also need to specify maybe FOV, right? So what's the field of view? The field of view is going to be, I suppose, 90 degrees, right? So FOV. So what is 90? It's half of a pi, I suppose, right? So this is a half of a pi, so this is a FOV. So I want to actually render that FOV. So let me see how we can do all of that. So we even discussed that on the scrapped session, scrapped online session. So this is basically the right triangle. So this is the right triangle. So FOV, we kind of know this angle alpha, right? So we know this angle alpha. And it's basically half of the FOV, right? So we can just say that this is FOV, right? I'm using mouse, by the way, mouse to draw in here, right? So, and if we take the tan of alpha, we're gonna end up with basically a ratio between opposing side and adjacent one to the angle, right? So opposing is this value that we're probably interested in, right? We're interested in this length because once we know it, we can quite easily jump to here, right? And then knowing the length, we can jump to here, effectively finding this point, and it's super easy to find the opposite point. You just jump in the opposite direction by the same amount, right? So when you have 2 points in here, and now you can actually start shooting rays super fucking easily, right? So it's very straightforward. You can take 10A, and since it's this ratio, right, and you want to find opposing, you know adjacent, right? This is near clipping plane, right? So that means you can just multiply that by near clipping plane NCP, right? And effectively you will cancel out the adjacent thing, and you're gonna end up with opposing ones. So you're gonna end up with this sort of length that you're interested in. So yeah, that's essentially what we effectively have to do in here. So to find the correct thing, let me try to do that. So math 10, and this is FOV, half of the FOV, and we'll multiply it by the near clipping plane. So there we go. So that's the sort of like a length of one of this arm in here, right? Of this sort of like arm. And I'm thinking, how should I call it? So maybe I'm gonna call it just L, but I'm not 100% sure. So what is this one? So this is a thing right in front of the player, right? This is a thing right in front of the player. So this is a player position, and we have a thing right in front of it. So I'm not really sure how to call it. So I'm thinking to call it just P, right? So this is just that. Interestingly, I think I'm gonna call the left sort of arm and right arm like P1 and P2, or maybe PL and PR correspondingly, like P left and P right. But in any case, I need to essentially take this vector, right? I need to take this vector that I have and rotate it 90 degrees. So to rotate a vector 90 degrees, it's actually super easy, right? So if you have a vector x, y, to rotate it 90 degrees, you can just take minus yx, right? It's super freaking easy, and it's gonna have the same length. So maybe we can have a method in here that just does that, so we can chain things together. So let's say rot 90, and it's gonna be vector 2. So we're gonna return new vector 2, this y minus this x, right? So that's pretty cool. Yeah. Okay, so I can now take P, rotate it 90, normalize it, and then scale by L. But to do that, I obviously need to have this kind of thing. So this is also something like this. So this is one of these arms. Is it? Oh yeah, I never called it actually. So this is P1. All right, this is P1, and I probably want to render it somehow. So I'm rendering things from position to P, then, so my neighbors are doing something weird. So from P to P1, and let's see if it's gonna be like a left side. Oh, Jesus fucking, okay, this is the, yeah, so this is not the direction vector, right? So what we have to do, so if I remove this thing, this is the correct position, so I need to subtract one from another. So what I have to do actually is subtract player position, right? Subtract player position, rotate 90, normalize scale, and I guess add player position again. So that's probably what I have to do in here. And that will give me kind of that, but that fucking sucks. Maybe I should have not added that. Yeah, I think I should have actually added P, not P1. Finally, Jesus fucking Christ. Okay. So, and I suppose, so this is just that, and maybe I should have added it in a different order, right? So I just add it like that, because now if I want to do P2, I just have to subtract it. Yeah, there we go. That's what I'm talking about. So there's another thing I want to draw in here, is just basically player position, P1 and P2, so that connects all of that together. So yeah, we can increase the distance of the clipping plane like so. We can also change FOV, we can make it narrower, but I think 90 degrees is the optimal one, but I'm not sure about the clipping plane or anything like that. So that's pretty cool, isn't it? So yeah, so this is how we find P1 and P2 given the player position and the player direction. So that is actually super cool. So now what we have to do is interpolate from this side to this side and start shooting rays in all of these directions and see what kind of things we hit in there, right? That's what we have to start doing. So I think what we need to do in here is, like, we have step ray, like ray step. So we have ray step. Do I need any of these functions in here? Because they take up too much space, but maybe I do, right? They're kind of useful. Yeah, they're kind of useful. What I want to have a function called cast ray. So it accepts P1, P2, both of them are vectors. And I suppose it also accepts the scene. So let's accept the scene. So this is a scene. And what I feel like it's supposed to return maybe a color, right, of the thing. So basically the color of the stripe that you need to render, or undefined if we didn't find anything, right, if we went into the void. Also, interestingly, so I think it also need to specify, I think it should return the vector, which is going to be basically the coordinate within the scene, so you can estimate for yourself, right, so like what's that thing? Maybe it should also return a vector too, basically the point at which it stopped. The point at which it stopped. I think it's a good thing, right? So the point at which it stopped. So yesu. And I'm gonna do new throw new error, and so what we're gonna do in here is just like cast array not implemented. So in the future, I kind of plan to store colors instead of numbers in here. So maybe we can even do something like string or null, right? So it's going to be filled in with nulls if there's nothing in there, or if it has something, string is going to represent the color, and that's the color that we're going to display and stuff like that. And I think it's really important to return a vector in case of the cast array, because we need to estimate the distance so we can actually draw the strip shorter, right? So it creates this effect of you know, of projection or something, or perspective, right? That's what I was trying to say, because the farther away an object, the, you know, the smaller it becomes, right? So it will also depend how exactly we want to interpolate things, right? So maybe there will be some sort of like a far clipping plane, but I haven't decided how exactly it's going to look like. Anyways, so this is a cast array, and all right, so this is a minimap. I feel like the player, how are we gonna approach all that stuff? I don't even freaking know. I kind of feel like I want to tuck away this kind of stuff behind the player function, because this kind of stuff is going to be useful in both yeah, in both minimap and actual rendering, right? So it kind of makes sense to just have some sort of a function within the class player that gives you P1 and P2. Right, so I didn't really know how to call this function, but it basically returns you these two vectors, like P1 and P2. So let's move this entire logic in there. So what is this for? There we go. So I can replace player with this very freaking easily. And we can just return P1, P2, that's it. So now I can quite easily do something like const P1, P2, P1, P2, player foo. Right, and we don't even need that stuff anymore, like at all. In fact, I think we don't need any of these things, so we just need to connect P1 and P2. So we're kind of losing the middle one, but it's not really important, right? So we lost the middle one, but we can clearly see the, you know, the FOV, the FOV thingy. So I'm not sure how to call this foo. Right, so it's FOV range, right? So just basically, I don't know. So maybe that's what it is. FOV range, and we'll need that in 2 places at least, right? So we'll need that in 2 places at least. Okay, that's pretty cool. What is the other thing we need in here? So we need a function render, I suppose. It's going to be ctx. And honestly, I think that render thingy has to happen. Ooh, what's up with that? Number is assignable. Oh yeah, I modified types in. Yeah, so it has to be. Yeah, that's fine. That's totally fine. So we pass this thing in here, and also probably the scene. Yeah, there we go. So we're gonna have a render. Let me grab this thing. So it's a canvas. So player and the scene. Okay, that's cool. So, and in here we can quite easily already do P1, P2, player FOV range. And there we go. So we can now start interpolating from one point to another. We can start interpolating it. So I suppose to be able to interpolate it, right? So we probably want to have something like lerp P2 and just like parameter here from 0 to 1, maybe half or something. Right, and let me quickly implement that. So lerp that vector2 t number, and we're going to return vector2. So what we're doing, we are basically subtracting this from that, and we're scaling it by t, but then we're also adding this back, maybe like add this. So that's basically going to be our lerp. That is our lerp, that is our lerp. Though I could have done that myself without the lerp, but I mean, that's fine. So to be fair, like rendering, doing array casting at a high resolution is probably going to be super slow, right? Because you have like a lot of columns. So I'm thinking that I'm going to have a smaller resolution, right? So let me think how I'm going to approach this entire stuff. So I'm going to say, we're probably going to have something like a screen width right? And the screen width is going to be like how many of those things we want to have in here. Let's say we're going to have 100 rays from there. Right. Okay. So 100 rays. So where's the render function? Here's the render function. So that means I'm basically iterating from 0 to screen width. I might as well actually call it x, right? So I'm just calling it x plus x. Okay, so, and in here, I'm going to be interpolating like this, right? As you can see, I'm interpolating from P1 to P2. And that's essentially the thing I have in here. So since it's a range, I want to kind of call it maybe R. Like it's R1, R2, R1, R2. And it doesn't really matter that much, so let's call it P. So essentially, I basically found one point in here. So I'm just slowly iterating through all of these points in here. And each of these points gives me sort of the next point for the array. So the array begins at here, and it continues at here. And this is where we have to cast it and step it and so on and so forth. Right, so, and this is what we have to do. So if, where is the cast array? So that's what we have to put in here. So we cast in the array. So we pass in the scene, and P1 is going to be the player position, and this one is going to be just P. Right, since it's such a small thing, we might as well, you know, just do something like this. And we have some sort of a result of the array, right? And so this is where it hit. So maybe this is what we're going to call P. And we can see whether this thing hit anything, right? So we have a function hitting cell. Right, so this is a hitting cell. Does it even hit anything? So in hitting cell, expect you to have a direction. So we do have information about the direction because we have this kind of stuff. Right, so, and yeah, so it only passed this to the sign, so everything should be fine. So this is a cell. So we have a cell. And we want to check whether we're within the scene. To be fair, we don't really have a convenient function to do that. So let me try to maybe introduce such function. It's going to be inside scene. So we accept the scene and we also accept the point. And then we just return a boolean or not. So we need to have a scene size. So this is the scene size. So this is the size. And the result is basically size px is greater or equal, or px is less size x. Right, but maybe it could be equal, but I mean, that's totally fine. And we repeat all of that stuff for the y. And that's basically it. So if it's inside of scene, it's going to do that stuff. All right, so we get that. If inside scene, we basically want to check whether we have something within the scene. So, to be fair, since we only have like walls and stuff like that, yeah, so we want to do something like scene, cy, cx, and if it's not equal to 1, we are going to draw a specific sprite. Yeah, we're drawing a sprite. Okay. We need to take the canvas width, right? The canvas width. We need to divide it by the screen width. And here we get a strip width, I would say. Strip width. That's what it is. Because we're drawing strips, right? So we have 100 of them. Yeah, 100 of them. So this is a strip width. And if we found something that is not 0 in here, right? So if we hit something that is not 0, we have to draw a strip, right? So let me see how we're going to be doing all of that. I think I can just do this thing, fill rect, So in terms of x, it's going to be basically x multiplied by strip width. In terms of y, it's going to start at 0, 0. Okay, so width is going to be strip width, and the height is going to be the height of the entirety of the canvas. ctx canvas height. So right now we don't really have colors of walls. We don't have colors of walls, and because of that I can just pick whatever color I want. I can say it's a fill style equal red. So I want it to stand out. Like I want to be able to instantly see that. Okay, there's something in there. Okay. And that's about it. We don't really take into account the actual height of the strip yet, right? So I just want to be able to see the colors and stuff like that. And that's about it. So the only thing it requires is implemented cast ray, right? So cast and array. So how we're going to be doing all of that, right? So we're going to do the infinite loop, right? So maybe while inside scene, while p2 is inside of the scene, right? And the scene p2y p2x equal to 0, we are stepping a little bit further, right? So we keep stepping. Step array, or ray step. So we specify p1, p2, that gives us p3. There we go. That gives us p3. And what we're doing here is just p1 becomes p2 and p2 becomes p3. That's actually pretty straightforward. And then at the end we can just do p2. So yeah, if it's not inside of the scene, it will go away immediately, right? So, and that's totally fine. Outside of cast ray, we actually check whether it's inside of a scene, and it's totally fine. If it's inside of a scene, but now this thing hit the wall, we also stop and we return the point where we hit the wall. So it's actually pretty straightforward. Once you have this array step function, it's just like, yeah. Okay, let's go through all of the errors. Potentially, there's no errors actually, so everything seems to be fine. So let me close this thing. Yeah, so there's no errors. Okay, so that's pretty cool. So anything else? I don't think anything else, honestly. So, okay, let's give it a try. Oh my god, I don't know what happened. I hope it's not going into the infinite loop. Oof. Okay, so what do we have in here? Undefined reading. So 24. So inside of cast ray, it's a JS24. Okay, so we probably need to have some sort of like a source maps. Is it possible for TSC to actually have source maps? Source map true. Is it going to automatically recompile this entire thing? Okay, so it actually picked it up automatically. That's pretty cool. So it's 136. All right. So cannot read properly. Oh, okay. I see. So this is rather complicated. Yeah. What we have to do, yeah. So we first have to find the heating. Yeah. So we can't directly do this stuff. So maybe because of that, we have to maybe do it like this. So so this is an infinite loop. We have to do C. All right, we got that. So do we have a player position? Yeah, no. Heating cell P1, P2. All right. So if this thing is inside of it, and if this thing not inside of the scene, or this thing not equal to 1, we just break out of this entire thing. I guess that's it. All right. So cool. I didn't see anything, honestly. Nothing works in here. Nothing works here at all. But I also don't see any errors. Let me see. So I have a hypothesis that maybe minimap actually cleans up something. Do we have? Yeah. So this is what's going on here, right? So minimap cleans up like entirety of the thing, right? All right. So I think it should do that in here. I think minimap shouldn't do this kind of stuff. Like I'm pretty sure about that. So, and in here, yeah, so it even does that before translation, and so, my god. Right, that's why we couldn't see shit in this mist. Okay. All right. So we can see something, I guess. So, which is actually like precisely in here, right? So, that's pretty cool. Let me now try, okay, put something maybe behind the minimap, right? After we did the entirety of the translation, right? Let's actually put something behind the minimap. And I wonder how we're gonna do all of that. So it probably takes into account the grid size, yeah. So fill rect, ctx fill rect, maybe ctx fill style, let's put this stuff in here, is equal to 80, 80, 80. And we're filling the rect. How we fill in the rect? We're filling essentially 0, 0, and then we take the grid size and we spread it. I think that's what we want to do in here. So I just want to have some sort of a backdrop for the minimap. So, and then I want to reduce the size of the minimap so it doesn't take up the entirety of the thing. Okay, so that's pretty cool. So it's somewhere there in the corner. So if I'm gonna start maybe rotating the player, I'm gonna start rotating. So now 80 degrees. Okay. So it's kind of to the right. So I would expect this thing to be to the right rather than to the left, which means that we have a FOV range problem. So I feel like I need to swap this thing. So this has to be sub and this has to be add. Yeah, that makes sense now. Right, so that explains the whole thing. And now, so if I take a half of this entire thing, I can't see anything. That is actually pretty cool. All right. So let's go back into that stuff. So this is that, and then another half. This entire thing is kind of in the middle. I want to put it in the middle. Yeah, there we go. So we're looking precisely at that thing. Damn, what the fuck? So, all right. So we have to kind of compute the distance between those things. So we have a rendering, render, and so we got the scene and stuff like that. And we can try to compute the distance. So I take P and I subtract player position from it. And I just take the length of this entire thing. Cool. I get the length. But then how do I decide how small this entire thing is going to be? So I need some sort of like a far clipping plane, right? So how much is it going to decrease or something? At which point it's going to become invisible. Okay, so let's do far clipping plane, and I think it's going to be maybe around 10 or something. Maybe that's going to be fine. Far clipping plane, and it's not really like you have to subtract like near clipping plane, right? So maybe not. So I'm going to divide that by far clipping plane, and that gives us an interpolator, which we have to use to determine the height of the whole thing. So I suppose 1 is going to be the full height, right? I might as well just multiply it by that, and that's basically the height. But I can use the height in here, but I also have to align everything correctly. So x is going to be just fine. Here I have to take the height, and I'm going to position everything at half of the height, but then I'm going to subtract half of the strip height. Right, something like this. Not sure if you can see that, but there we go. Maybe I should call this strip height, so because we have a strip width already, yeah, and then with strip height. Const strip height. Okay. So can you see what I'm doing? Strip height. Strip height. Strip height. And I can maybe, I still don't know how you call this operation when you have two things multiplied by the same sort of coefficient and you move that coefficient out of the parentheses. It's like a distribution, but it's an opposite of distribution. Redistribution, like I don't know how, like I don't know the terminology in English. I know terminology in Russian, right, but I'm not in English because I never studied math in English. Like I mean school math in English, right? So studied some math in English, but not the school one. All right, so we want to probably do something like this. Hopefully that will create the illusion of perspective. I think it has to be, that is absolutely bizarre. So it has to be the other way around, I guess. Yeah. No, we didn't. Oh yeah, I know what is going on. Yeah, there we go. So there's some sort of a warping going on, which is kind of cool, honestly. Which is kind of cool. I wonder why though. Was there any warping in the original raycasting? Though maybe this is because of the like a pretty nasty resolution. So, or maybe it's also because of FOV. So because this thing is just like a straight of that. But yeah, I think I should be able to maybe modify the player's, what is it called, direction, right? So I think that's a good idea generally. But can I make these constants? Yeah, so this is a constant. So player, I'm going to be modifying the player, but since I'm not reassigning the player, I think that this thing can be constant as well. Anyways, so we need to add a listener. Game add event listener. Do we have something like key down or whatever? Let me find key down. Key down. All right, so we can probably work with that. Key down. But probably we don't want to do that on a game. We want to do that on the whole body. All right, so can I just do body? I probably need to find the body, or maybe document. Can I do add listener? Oh, window. Yeah, window. Just a second. Yeah, but the document, does document have that? All right, so it looks like document does have that, but probably window is going to be better. I'm not a web developer, I'm sorry. Right. Please forgive me. I'll figure it out. Don't worry about it. I will figure it out. So, what do we have in here? Maybe I want to just like console log this thing and just see what is going on. Yeah, there's some sort of warping, so maybe I just like actually set the height of this thing incorrectly, but that's fine. Okay, so I do key, but it's repeating itself, right? So key down. That is a little bit bizarre. Window event and the global event key down and key up. Yeah, I'm not really sure why on key down it repeats itself. That is absolutely bizarre. Why did it repeat itself? So maybe does it tell me whether it's repeated or not? Yeah. Oh yeah, repeat true. Okay. So that's fine. But I wouldn't expect it on key down. That's really bizarre. But anyways, so what do we have in here? I can also have key up. If E repeat, not repeated. And also probably here as well. Yeah. All right. So yeah, I can detect with the key up, key down. So, and I also have key code in here. I'm not sure which one to use. Maybe I'm gonna use key code. So it's not repeated, and we need to check it's not repeated, and E code equal to key D, right? So in that case, I just want to say that we're rotating to the left, right? So maybe we're gonna have rotate right, which is gonna be false, and also we have rotate left. All right, so if maybe what's the switch case? Let's do switch case. Case that. So if it's that, rotate right true, break, rotate left, cool. So now if we do that, we do rotate false. Maybe I can even realign some of these things like that. Look at that, look at that. So, and now, as we're holding them, so we need to organize actually sort of like an event loop, right, where we play in animations and stuff. Though I don't want to do it right now. So maybe I'm gonna do, yeah, I'm gonna just do just that. Let's get rid of this stuff. And I'm going to say that you pressed KD. I'm going to take the player, so that means I need to put the player above the window. I'm going to put it above the window, and I'm going to take the direction, and I'm going to just add some sort of angle, which is a math pi multiplied maybe like, I don't freaking know, like a 10th of a pi or something. And in here, we're also going to do, so we can correct the direction a little bit later. So, and every time we modify this entire thing, I feel like we have to basically re-render literally everything. So let me put this stuff in here. So this is the first rendering, and this is going to be the second rendering. So I just don't want to do animation stuff. Don't want to do animation stuff. Okay. Do we have any scheisse in here? Okay, so that seems to be fine. All right, so yeah, that's pretty cool. I wonder if I can set the clip in plane even further away. Yeah, the further away I put it, the better it looks. So one of the things we can do, okay, so let's actually increase the resolution of the whole thing, right? So yeah, I can increase the resolution quite easily, as you can see. So, and strip width, can I maybe even just make it a little bit bigger, like add the epsilon so they overlap with each other? That would be kind of cool. Can't you? Because I feel like they're a little bit bizarre, right? So so I want them to overlap a little bit, so it's kind of weird that they're not overlapping. So yeah, strip. Maybe one of the things we want to do, so when we do the division, maybe we want to do actually seal, so they overlap with each other. Yeah, boy. So I'm gonna actually save this thing to some sort of a parameter t. So because then I can use this parameter t to modify, like to shade this entire thing, sort of speak. Can't I? I think I should be able to. Can I use this template thingy where I would say RGBA and just like 255, 00. I think 1, I don't quite remember. I think alpha is the only one that is 1, so to speak. But anyway, so here I can just say 255 by t. So, and now, yeah. So now it's just like shades it more or less properly. It just kind of shades it in some way. All right. So it's pretty cool. So if I change the far clip in plane to be a little bit closer, right? So that looks kind of awesome, honestly, even though it's warped. And I don't really know how to make it less warped. It probably has to be. So maybe I should consult the tutorial. How exactly do they do that? Yeah, just a second. So because there's a lot of text in here, so the screen height. So the color. So this is already like texture. Okay, so this is the thing. Read keys. They don't. All right. Vertical line. Draw start, draw end. This is where they do that. Draw the pixels of the stripe as a vertical line. Okay, so where do they do draw start? I wonder. Draw start. Okay. So calculate height of the line to draw on a screen. Height versus perp wall distance. Huh. So that is interesting. I don't really understand what it means. So there's such a holy fuck. Alright, so I suppose this is the position of the player, right? So oh, okay. Ooh, I see. So this is Euclidean distance, and this is h, and this is a perpendicular wall distance to this kind of thing. But how do you compute that? That's a good question. That's an interesting way to do that. So I suppose this is the h, right? So and perp wall. All right, so let's actually find it. So that will be used later to calculate the length. How do you compute that though? Side distance, delta distance. Okay. Calculate the distance from of a particular ray. Euclidean distance would give. Okay. Euclidean distance would give a fisheye effect. That's actually rather interesting, right? So. Side distance, delta distance. I don't fucking know how to do that, honestly. Right, so I need to think about that, honestly. I need to think about that. Side distance. Yeah, maybe I'm gonna just keep the fisheye effect for now, right? So because I already spending too much time on this kind of stuff. So what I want to do, honestly, I want to maybe factor out this piece of code to everything. So it's called the render, but I don't really know if it's a good name for this kind of thing. So this is a minimap, this is a render, but then how do I call this thing together, render and minimap? So I would like to call it a render, but this one is, let's call it maybe game, right? So this is actual game. Right, so this is a next error, this is a game, this is a next error, this is a game. Okay, so then, it's we already have word game probably. Oof. Render scene. All right, so let's call it render scene. Render scene, render scene. Okay. Query replace minimap, render minimap. No. Yikes. Render minimap. Yeah. And now let's introduce render game. Render game. So, and what we'll need in here? CTX. Understandable. Canvas. What was the canvas? What is it called? It's not. Yeah, canvas rendering context. Canvas rendering context. The player, and the scene. So minimap shit. Can we compute minimap shit somehow differently? Yeah, I think we can move computing the minimap into here, into render the game. Yeah, so that makes sense. So that way now I can just say render game. And this is just the parameters that I need to pass in there. CTX, player, scene. Right, and all of the parameters for the minimap is going to be computed inside of it, so none of that matters for us that much. Yeah, so this is the game, this is that. There we go. So that simplifies everything dramatically. I want to be a little bit of like a C developer. Right. I don't know if for some reason. I just want to do it like that. This looks cool. Nice. By the way, I think I want to keep player and the scene together in like in a single place. Oh, this is where we had a name game. I see. So that's understandable. That's understandable. All right. So I like how compact this entire thing became. Right. It's just scene, the player in a particular place with a particular rotation and stuff like that. Do we have any compilation errors? We don't have any compilation errors. Right. So fish eye effect. Maybe it's even fine. I'm not really sure. So we'll also have this sort of like a, I forgot the name. It's just like the shading based on the distance. There was a fancy name for this kind of thing, but I'm a dumb, so I don't really know. So maybe we need to introduce like something like movement. Key W, right, is going to move forward. So to move forward, what you have to do, you probably have to take the player position and also player direction, right? You're taking the player direction and you're constructing a vector from the angle and maybe scaling it by the step size of something, player step size, step length, right? And then you just add this entire thing to here, right? You just add it. And I suppose you also reassign the player position to that. So we need to have this kind of thing, and let me see. So maybe a single step is going to be like a half of the cell, right? So half of the cell sounds reasonable, I think. Yep, and every time we do that, we're going to re-render the whole game. Might as well now do stepping backwards. So instead of adding, we're going to be subtracting this thing. All right, so that looks reasonable, I think. It's pretty cool. Might as well just make this kind of stuff shorter. Any errors? No mistakes. Okay. That's so fucking cool. I need to get rid of the fisheye effect, honestly. Right, so I have a little bit of a time, so I can probably figure out how to get rid of the fisheye effect, but yeah. So this is me going towards this entire thing. Yeah. So I can even assign different colors on this thing. So let's go ahead and assign different colors. So scene is going to be like a either string or null. Right, so that's what I'm thinking about it. So next error, scene is not equal null. Right, so next error, scene size. So what you don't like in here, number is not assignable. Oh yeah, because this scene is not that scene, right? It's still array. Found this error. Okay, next error. Not equal to null. All right, so that means we have to fill it with, yeah, just the scene color, like this. Oh, this one is actually kind of cool. So what you don't like in here? I understand. String or null? Dude, oh my god, TypeScript. Checking this shit like that was not enough to strip off null from scene. Oh my god. Insane. Right, so the thing I have to do in here is just like, oh my god, type system of TypeScript. I have to do something like this. If that, only then it will strip off the null from. Okay. Very well then. So might as well do a similar thing in here. So this is a color not equal null. And this one is rather interesting, right? So how can I shade the colors and stuff like that? I can't really do that easily, so I guess I'm gonna just yeah, we'll have to disable the shading. Yeah, so there's only one way to do that. Next error. scene size. Okay, so this one is not correct. So the thing we're gonna do in here is basically query replace 0 with null. Boom. Which kind of sucks, but I mean, I don't really know what to do with that. So query replace 1 with red. Okay. Can I now maybe align some of these things somehow so they look more or less fine? Like this. Alright. Shut the fuck up. Shut the fuck up. Okay. So red, green, blue, yellow, magenta, maybe purple, cyan. So I just want to have different colors in here. Any errors? Okay, so that's cool. So now, yeah, there we go. Oh, I don't fucking know what the fuck is going on in here, but at certain angles, the minimap has disappeared. I don't know why, I don't know how, but it just disappeared. Maybe there's an error going on somewhere. Just a second. Oof. Okay, so 2021. Why? Okay. Damn, bruv. Damn. Okay, so essentially we first have to check that we're inside. Alright, if so, and if we are inside, only then we're doing that. Okay. Makes sense. So now that seems to be working. That seems to be twerking. Yo. Okay. Yeah. That's pretty cool. That's so fucking cool. Oh, it's funny how we can't see shit if we're outside of the whole thing. So I'm looking at the red and a little bit of a green. You can clearly see that here's the red and there's a little bit of green, and we can clearly see them. I'm looking inside of this thing. Yeah. So I want to get rid of the fisheye effect. Also, we can keep increasing the resolution. Alright, so we can give even more resolution so it's smoother. But I feel like, yeah. Oh, it's... I really love that. This is so fucking cool. This is so nice. The math is nasty. The math is absolutely fucking nasty, mate. But I mean, it's kind of cool. I can see actually improving that further. So fisheye effect. So perpendicular wall. I need to figure out what the fuck is that. So it's actually encountered like 26 times. This perpendicular distance is called perp wall in the code. How can we even... Yeah, I understand how you can do that. Right, so you have this point, you figured out this point, and you have Euclidean distance. And then, how can you figure out that? I'm really curious. So, yeah. Calculate distance projected on the camera direction. Euclidean distance would give a fisheye effect. Size distance x, delta distance x. I have no idea what the fuck it is, honestly. So where to get them? And also, what is side 0? Here's the thing, like I never really read and like get familiarized with myself with the terminology of this paper. I just look at the pictures and I just replicated the pictures. So I don't know what is a side distance, all of that stuff means. So depending on whether the ray hit an X side or Y side, the formula computed using side distance X or side distance Y. I have no idea. Okay, so delta distance, like I would appreciate them show what is it equal to, but I don't know. But maybe we can figure it out somehow. Because I don't know, I can do something stupid, like I can always find this point, if you know what I'm talking about. I can always find this point. And to be fair, I do know this point. Right, I do know this point because it's the point of like R1, yeah. I mean the line, right? So I have R1 and R2. So what I need to do, right, I need to figure out the equation of this thing, linear equation, which is really easy. You can compute the slope and stuff like that. And then once you've got the point that you hit, you just project. Yeah. So you have a certain point, you have a certain line, and you just need to find the distance between that point to that line, to the line that is represented by these 2 points. And that's the distance you're interested in, and that's the perpendicular distance. So we already have everything to kind of find that. The only problem is that I don't know how, given 2 points that describe a line and another point, find the perpendicular projection. Right. I can try to Google it up. Okay, so maybe I can ask ChatGPT, honestly. Maybe ChatGPT is actually perfect for this kind of stuff. Right, but I don't know. So let's go to DuckDuckGo. All right, so how should I have 2 points into this space. Maybe I'm gonna actually type that in Emacs. I have 2 points into this space that define a line. I have 3rd point. How to find its perpendicular distance to the line. I think that's a good prompt. I think that's a good prompt. So here we go. To find the perpendicular, please use Python code instead of later. Like the front end can't render anyway. All right, so distance points to line. All right, so here is 2 points, and this is that one. Okay, we're finding delta y and delta x. So for some reason, ChatGPT decided to actually call it A and B. And so then we finding the dot product between these 2 things, right? So this is the dot product between these 2 things. Okay. Holy shit, that's that's a very interesting way to do that. Okay. Is that even correct? So you have delta x and delta y, and then the dot. It's not even dot product, isn't it? Right, so because it's a minus. Damn, where did you get that idea? To find perpendicular distance is the so this is equation. So ABC, it's a equation of the line. I see what is going on. I see. You're figuring out a different kind of equation of the line, right? So that's what is going on here. Right? Different kind of equation of the line, and then you find. You plug in the point that you want to find projection for into that equation, and you divide it by the length of this sort of vector. All right, that's a very interesting way to do that, I guess. Okay. All right, rewrite. Like, I really want to understand that. I don't want to copy paste that. So ABC. It's kind of interesting how, like, the point is not on the line. That's the thing. The point is not on the line, but we plug that point into the equation to get some sort of a value, right? And by dividing it by the length of this sort of like vector, by the length of this vector, we find in that distance. It's a very interesting way to do that. Okay, so rewrite this in TypeScript. Not really this, but rewrite this thing in TypeScript. I wish I could spend more time to understand this thing a little bit better, but I'm already, this is the 3rd hour, that's why I'm gonna just like copy paste this thing, right, and just use it in here. I'm probably gonna regret that, but who cares? So okay, so let me take p1 vector, this is p2. It's not that different from just copy pasting from the internet. Just copying, okay? I'm just copying. All right, so this is that. So p2. P. All right, so this is that. Okay. I wonder if I can somehow bulk replace all of that stuff, but it feels like I can't really. Can't really bulk replace all of that stuff. Yep. And that's the last thing. By the way, can you actually do this kind of thing in TypeScript? ChatGPT. What the fuck is this shit? Let me see. So node 210. Oh, you can. I thought it's only a Python thing. All right, all right. Cool. I'll need to spend some time studying this like formula and why it works, if it works at all, because I don't know, maybe ChatGPT confabulated this entire thing. Who knows? You never know. So distance point to the line. So essentially, yeah, so we figured out this entire thing, and we just do distance point to line, R1, R2, and the point is P, essentially. So that's basically that. So we can even use perp wall distance. So maybe it's not as efficient as it is in the original paper, but hopefully it is going to work. So, and in here, what do we do? So let me see how we're using this entire thing. So remember, it was used in a very specific way. So H is the size. So line, I'm gonna just, like, I'm not sure if it's H is that. Like, what is H exactly? Calculate the walls has point. Oh, that's fine. Whatever. Line height. So what is H? Then out of the line height, which is thus height of the vertical, the stat in that position where we'll find drawn. I don't like that it doesn't tell me what the fuck is perpendicular wall distance. Perpendicular wall distance. Is that the full length or what? So I suppose maybe it's a height. It's a height of the screen. Yeah, probably. That's what it is, probably. Maybe it's a height of the screen. Yeah. Alright, so we have to take the height of the screen. But it doesn't make any fucking sense if it's a height of the screen. Is it not? No, it doesn't make any fucking sense. It's like there's a lot of like text in here, and it's just like I don't want to read that. Just tell me, oh my, especially this thing. Like, dude, like, no bueno, no bueno. It's just like, just show it on the picture. So I suppose maybe we just have to use perpendicular wall distance instead of this thing. Maybe that's one of the things we can do. Yeah. So let me see if it actually fixes anything. So that's the consequences of doing your own thing, right? So, but I really want to do my own thing. All right, it's just like super important for me to do my own thing so I can understand shit. I think, yeah, there is still a little bit of a fisheye effect, I think. It's not particularly helpful. Right, so there's also this curve and stuff like that, so it's not helping. So hit point of the ray on the wall. Okay. but it's a capital H. Alright, there's a mentioning of 2h. You can of course also multiply it by another value, for example 2h multiplied by h. What is h? I don't see. Now that we have a calculated distance, we can calculate the height of the line that has to be drawn on the screen. This is the inverse of per and then multiplied by... What is h? The height in pixels of the screen. Alright. H, the height... Okay, Jesus Christ, bro. Oof, this is really hard to read. Like, people told me that this is the best resource on raycasting, but it's so terse. Like, how... This is... Oof. Yikes. But I mean, thank you for providing it for free for everyone anyway, but I mean, oof. That's straight up gatekeeping, I'm telling you. But thank you anyway for providing it for free for anyone. So anyways, so what do we have? So we have that. So it's yeah. So what's the height? But making it height isn't it too much? Maybe it's not. Okay. So let me try to just take CTX canvas height. So that's what it is. That's what H is, I think. Oof. Yeah, that is not bueno. So maybe because, yeah, maybe I don't have to do it. Oof. None of that works. None of that works. So that should be enough. So calculate the height of the line to... Yeah, like I don't think it's good. Maybe it's just the screen has to be like smaller. I'm honestly perplexed. Like, what the fuck? It doesn't make any sense to me. So it could be that maybe there is a mistake in perp wall distance. I can see that. So maybe ChatGPT actually lied to me. I don't freaking know. But I just couldn't figure it out. So I need to somehow... So yeah, like I found... It doesn't make any sense to me, honestly. It doesn't make any sense. Why does it have to be like that? But what if I... Yeah, I'm already spending 3 hours on all of that. So I think I'm gonna leave fish eye effect for later. Right, so... Because again, it's already 3 hours, right? I'm telling you, this is what I was talking about. This problem is way more complicated than you would expect. Right, you can explain raycasting very easily, like on a piece of napkin, but then when you sit down to implement this shit, it's like, holy fuck. And it's only the first part of the tutorial, right? It's only the first part of the tutorial. Oh boy. Okay, so I think I really want to fix the fisheye effect. I really want to fix it because it's the video is not complete if we don't fix it. So I think I need to make a small break. Maybe refill a cup of tea, right, and go for another hour. Right, so let's go ahead and do that. This is the next day. I got so tired yesterday that I decided to continue tomorrow. Right, so after sleeping a little bit and also thinking, I just realized that I could have just utilized dot product in here. Right, so essentially, we have a position of the player, right, and we have an object that the player is seeing. Right, so here is the ray through which the player is seeing this entire thing. So let's actually call it something like V, I don't know. So, and we also know the direction where the player is looking, right? So let's call it maybe D. So, and essentially what we want to find effectively is the length of this thing, right? Of this sort of like vector which is extended in the direction of the player, where player is looking. So it's actually called maybe something like big D. So small d is just the direction, and big D is the whole thing that we're interested in, and this is the you know, the distance that we have to use to compute the height of the strip that we're rendering there. Right. So if you take a look at what is a dot product of two vectors and how it's related to cosine. So this is the most important part. It's related to cosine. So dot product. I wonder if I can just go to Wikipedia where we can see the definition of dot product. Wikipedia being gatekeeper. Yeah, this is what I want, right? So this is what I want. So let me actually maybe go somewhere here. So if we find the dot product between V and D, right? So basically the array and the direction where the player is looking. What effectively we're getting is a cosine of an angle between them. This angle, right? So let's actually call it alpha, right? So this is alpha angle. This is alpha multiplied by the length of V multiplied by the length of D, right? So, and what's funny is that if you take a look at the definition of cosine, cosine and sine, the cosine is alpha is adjacent side of the triangle over hypotenuse, right? So that means the cosine of alpha is equal to adjacent. What is adjacent? Adjacent is big D, right? So that means it's length D over length of V, which is a hypotenuse. Right, so and if you basically take and substitute all of these things in here, right, so you have that dot VD, which is equal to this, which is equal to this, right, so we can basically substitute cosine now, like so, and you will notice a very interesting thing. So essentially you have division by length V and multiplication by length V, which effectively get rid of this entire thing. And what's funny is that length D, so we know length D, it's just a direction, but we can easily construct this direction vector with the length equal to 1. So we can effectively ignore this entire thing. So essentially, if you take the vector of the array and do a dot product with a normalized direction vector of where the player is looking, you get the wall length, like literally the thing that you actually need. If you go through this entire logic, it actually does make sense. Right, so yesterday I couldn't think about that because I was super tired and I also asked ChatGPT and stuff like that. Anyways, so let me go ahead and try to implement that super quick. So we need to have a dot product. As far as I know, we don't really have a dot product. So we're going to have that, which is a vector2, and it's supposed to return a scalar. Right, so in here we're going to do this x multiplied by that x plus this y multiplied by that y. There we go. So this is the dot product. So, okay, so here's where we're rendering the game. Where do we render the scene? There you go. Okay, that's pretty cool. So what we need to have the V. V is essentially, so P is a point that hits the wall, that hits the wall. So, and we need to subtract the position of the player. Right, there we go. So this is V. So the direction vector is basically player direction, right? And we have to construct a vector out of that. So we're going to say from angle, like so. So, and then we are taking a dot product between these two things, and that's the value. So in the original article in here, so the way to compute the line height is just to take the height of the screen, right? So if I remember correctly, this is the height of the screen. Yeah, so the height by h, the height in pixels of the screen, okay, and divided by that value, and that value is that dot product. So let's go ahead and just do that. So this is a strip height. We don't really need t anymore, right? And we take ctx canvas height and divide it by that. So hopefully that is going to, yeah, there we go, it worked. So, and that fixes everything. That was actually easier than expected. Yep, we've got a Ray Caster. Congratulations. There's something funny about this Ray Caster, actually. Look at that. So you can see the purple cube between the cyan and yellow one, and I have a feeling this is due to how we compute the epsilon, right? So because we have a little bit of an epsilon to just adjust things around. So if I make the epsilon like way smaller, I think, yeah, I think that thing will go away. Just a second. Yeah, I think it was due to the epsilon. Yeah, that's actually kind of funny. It's actually kind of funny. So the epsilon could be very, very small, actually. Damn, this is a pretty sexy ray caster. Look at that. Look at that. All right. So yeah, I guess that's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all on next recreation programming session with Mr. Azozin. I don't really know if I want to continue developing this raycaster. Like, implementing texturing would be interesting. Also, implementing walls and ceiling, kind of interesting, right? Like walls and ceiling, I think is kind of similar. It's just like instead of vertical scan lines, you have horizontal ones, right? So we'll see. The winner gets the, that's for sure. All right, love you.